All right, welcome back everybody to day 2 of Car Hacking Village at DEF CON 2020. First up today, we have Automotive in-Vehicle Networks with Camille Gali. He's going to be talking to us about what types of networks we have in vehicles, how to get started hacking in this area, and a really interesting talk. Please join us on Defcord. We will have the Defcord channels open, so please join us. Ask questions in the Discord CHV101 support text chat or channel, and enjoy the rest of Car Hacking Village 101.
And welcome back everyone to another Car Hacking 101 talk for DEF CON Safe Mode 2020's Car Hacking Village. My name is Kamel, and in this lecture I'm going to be talking about in-vehicle networks. I'm also doing a talk for Bluetooth in the same kind of vein of Car Hacking 101 talks. So if you've already seen or heard my introduction, I apologize profusely, but I have to give it again for those of you that might not be interested in Bluetooth or just coming to this one first. So, very short speaker introduction, right? As I mentioned before, my name is Kamel Gali. I'm an automotive cybersecurity technology architect at White Motion. White Motion is a small automotive cybersecurity focused company. We're a subsidiary of Marelli. It's a much larger Italian automotive tier 1 supplier. It's actually the combination of the older Magneti Marelli Italian automotive tier 1 and a Japanese tier 1 called Calsonic Kansei. They actually merged a couple of years ago, and White Motion was at the time owned by Calsonic Kansei, and now we are a full subsidiary of Marelli Corporation. So I myself am based in Tokyo. I'm a trilingual car hacking enthusiast, as I like to call myself. Because for me, this is very much more than just a job. It is more than just a profession. It's something I enjoy, and I enjoy doing a lot of volunteer activities in the industry as well. For example, this Car Hacking 101 talk is not something anyone is paying me for. No one is, my boss didn't tell me to go do this. This is entirely because I enjoy what I do, and I think a lot of people would enjoy doing what I do, and I want to make sure that the knowledge is easily accessible for people that want to join the industry. So along those lines, I am an ex-admin of ASRG Detroit. I got involved in automotive security research group while I was living in Michigan, helping out with things like working on collaboration between industry and academia. And I'm the founder of the Automotive Security Research Group Japan. For any of you that aren't aware, Automotive Security Research Group is an organization dedicated to sharing information about automotive cybersecurity, making it more readily available, and mainly being driven by the community as opposed to, its own industrial entity, right? So it's a pretty open community, and a lot of, freely available talks, etc., are available online for anyone that wants to learn about automotive security. But anyway, I've gone on a bit of a rant there, but I like to consider myself a jack of some trades, a master of none. My recent areas of interest are Bluetooth, USB, radio frequency, digital forensics, and I have some interesting hobbies of mine that I have listed down below. But today we're not talking about any of these technologies. We're going to talk about in-vehicle networks. So what is an in-vehicle network? An in-vehicle network is, as I would hope is obvious, it is a network that's used inside a vehicle. Right. So it's a networking technology that's used to allow the ECUs inside a vehicle to efficiently and safely share information between one another. So these in-vehicle network technologies are designed specifically for use in these closed environments where you have several ECUs inside a vehicle. They need to share sensor information, the results of calculations, calibration information, vehicle status, so on and so forth, with other distributed processing units throughout the vehicle, right? If you consider, very broadly speaking, a network can be anything. It can be Bluetooth is a network, 4G, 5G, those are networks, DSRC is a network, Wi-Fi is a network. But for the purposes of this talk, I'd like to make it clear that I'm talking about physical networks. I'm talking about guided medium networks, right? For those of you with a background in networking, you might know the difference between a guided and an unguided medium for your network is that guided means it's got copper or fiber in place that actually, guides the transmission of information along a specified path, right? It's not radiated like it is in most wireless communications, right? So we're going to be talking about those kind of physical wire communications, be they copper-based or fiber-based, and how they're used in a vehicle. I'm going to go over some of the different types of in-vehicle networks that are found in the industry today. I'm going to talk a little bit about each one of them, how they're used, what their strengths are, what their weaknesses are, etc. Right? Strengths and weaknesses are a big part of in-vehicle networks because, as you can see, I have listed here, they are selected based on what role they fill for a given application, right? There's no one size fits all best in-vehicle network solution that can do everything. There are different solutions, different technologies available that manufacturers selectively include in their vehicles based on where they're most appropriate, right? You'll see how this works out in just a second. So, in the context, I was drinking some pineapple juice and some of it's got stuck in my throat, which is probably not a great way to get ready for giving a recorded talk. But in the context of a self-driving or autonomous vehicle, this is a fairly common, logical setup within a vehicle, right? In this diagram, we have a couple of ECUs alongside a sensor and some actuators, right? The sensor in this case could be, any number of things. It could be a camera, it could be an accelerometer, a CO2 sensor, a LiDAR sensor, user input sensor, radio, it could be almost anything, right? The sensor is, at this point in this logical diagram, we're just treating this sensor as a source of raw information, right? The data that this device generates needs to be processed. The sensor is intaking raw information, and that information needs to be processed. It needs to be interpreted by a processing unit so that the vehicle as a whole can kind of understand what that raw data means about the vehicle's environment, what it has to do next, so on and so forth, right? So based on what kind of sensor it is, what kind of data it's going to be producing and how much of that data it's producing is going to be different, and a different in-vehicle network technology might be chosen to carry that data from where it's generated to where it gets processed here in the ECU, right? So along this diagram, if we take it, kind of from start to finish, the sensor here is going to generate some raw data, right? This is going to be a camera that's facing, towards the front of the vehicle. It could be, just assume it's a camera, right? And it takes that image data and it sends it to ECU1 for processing, right? Because the processing power is going to be contained here on the ECU's microcontroller, right? So this line here is meant to represent an in-vehicle network, right? Because something needs to be in place for this sensor to be able to send that data to ECU number 1 over here, right? Once ECU 1 has the raw data, it's going to be able to do some calculations, interpret that data, understand what that data means, right? Is there, a traffic sign, a stop sign in front of us, a red stoplight, how in self-driving cars should stop for stoplights, so on and so forth. It's going to make those decisions and, understand the raw data it received, and then it's going to pass the results of those calculations on to another ECU, right? And then maybe this ECU is in charge of something else, right? Here I have, two very broadly defined actuators, right? An actuator in this scenario being any device that upon receiving, an input from a processing unit converts that input into a physical real-world stimulus, right? A thing that happens, right? This is what I mean when I'm talking about an actuator. So each of these lines here is meant to represent an in-vehicle network, and I have them all colored the same way because at this stage, I haven't talked about the different types of in-vehicle networks, but each one of these is likely going to be a different type of in-vehicle network technology because the amount of data being processed from here to here might be different from the amount of data processed between these two, and it might be different from the amount of data processed between, ECU2 and the actuators, right? So something to take in consideration when considering which in-vehicle network technology to choose would be things like safety and robustness requirements, distance from the ECU to the actual sensor, right? Bandwidth necessities, how much data is being processed, what kind of data it is, how fast it needs to be processed. All of these are metrics you want to take into consideration when picking the appropriate in-vehicle network to use, right? So going on, we're going to talk a little bit about network topologies and how they relate to in-vehicle networks. So I have here, I ripped this image from the internet somewhere. I have the source listed down here. This is a look at a couple of common network topologies, right? You have your mesh network, you have your fully connected network, which is also called a full mesh network, right? You have star topology, ring, and a common bus topology. These might be pretty familiar to you if you've worked as a systems administrator, or you have any, experience as an actual networking engineer, right? Some of these will be familiar. And how they relate to in-vehicle networks is that where am I going with this? Okay. Most of the in-vehicle networks that I'm going to talk about today will use a common bus topology, right? But that doesn't mean that there aren't some that use other topologies instead, right? Because in-vehicle networks are designed to be reliable and robust, because they are, part of a vehicle ecosystem. A vehicle is a moving object that moves very fast, is very heavy, and has living, breathing people inside it. There are a lot of important, safety thresholds that need to be met. There are a lot of standards that, are in place to best guarantee the safety of the passengers and the environment around the vehicle. And so when we talk about things like the networks that we use for transferring this information, it's important to know that they need to be designed with a level of robustness and reliability and safety in mind, right? So with regards to the networks shown here, some of them have strengths and weaknesses that are realized, or I suppose they can be seen in the vehicle network technologies that make use of these topologies, right? So say you have a fully connected network. This is a very expensive, very hard to implement type of network, because every single unit in this device is going to have a direct link to every other unit in the network, right? This means you need to have the hardware and infrastructure to connect every unit to every other unit, right? And the positive to this is that you have incredible redundancy. If any link goes down, it doesn't matter. Every computer has a link to every other computer, or every other processor, right? Every other microcontroller, so on and so forth, whatever it could be, right? So if this ECU here, let's pretend these are ECUs and not desktops. If this ECU wants to communicate with this ECU, but this direct link between them breaks, right? The obvious logical conclusion is then, well, I can still talk to this ECU, but through any number of other paths. I can go from him to him, I can go from him to him, or from him to him, or from him to him. The fully connected network topology offers the most amount of redundancy, right? But the downsides are, like I mentioned earlier, they're expensive, they're sometimes a little bit more complicated to implement, and especially when it comes to cars, the actual physical cable weight is becoming a sort of rising concern for automotive manufacturers, right? The actual weight of the cable harness is not a trivial thing. It's not a trivial part of the vehicle ecosystem, right? The actual designing of a vehicle needs to take into account how much cabling is going to be in there, because you can have, I'm not, an expert on how much cable goes into cars, but I'd say it can amount to quite a bit of weight, right? A couple, maybe tens of kilograms, I would assume, right? This is just an educated guess, right? But I'm sure someone more familiar with that actual metric would be able to give you a more accurate number there. But those are the pros and cons of something like a fully connected network topology. A mesh network is kind of like a not full connected network topology. It's kind of like a in-between, right? You'll have different devices here with different connections to some, if not all, of the other processors in the network, right? This is good because you'll have some level of redundancy where if, say, this line goes down, right, then you can still reach this processor here by going, okay, we'll go here, here, and then here, right? So you have different paths that your data can take if you need to send data from one processor to another on the network. Right? Common bus topology, this is where all of the ECUs in this case will be connected to a single common bus that they can all send or receive data from at the same time. This is how CAN bus works. I'll talk about that in the next couple of slides. It's the most common in-vehicle network in the automotive industry currently, but this is a pretty common implementation because of how easy it is, right? All of the nodes are just connected to one network, and there isn't any kind of routing protocol you have to implement, especially when it comes to CAN, right? It's very simple. It's easy to get set up, and it works pretty well. But one of the downsides, and it's cheap, by the way, but one of the downsides is that this common bus then becomes a single point of failure. So maybe, you wouldn't use something like this in a very critically important system, right? Especially when we're talking about things like government systems or military systems, you're more likely to see something like this because they are prioritizing, in the moment operational stability over everything else. Whereas for a mass-produced vehicle, right, this is kind of how you want to go, right? It's because it needs to be mass-produced. It's not feasible to make every single car on the road in this, fancy of an architecture. Moving on, ring topology is pretty rare, but I believe that the most protocol, I'm talking about rare as in within the vehicle or context, right? Within the most protocol, I believe a ring topology is used, although there are different versions of most, and some of them might be able to be used in other versions. Most isn't a technology I've personally worked with a lot because it is pretty rare, but I will touch on it briefly in this presentation. And then you have a star network topology. This is one of the more common topologies, and especially when it comes to discussing technologies like automotive Ethernet and trying to run TCP/IP inside cars, right? Those are point-to-point protocols, and for that, a star topology makes a lot of sense. It's a very happy medium. It doesn't have an excessive amount of cabling, and it doesn't have if one of these links goes down, then the rest of the network is usually protected, but you do have to rely on something like a switch or something in the middle to handle forwarding of communication between the different ECUs, right? But it's kind of seen as a happy medium network topology, right? But anyway, enough about topologies. Let's start talking about individual in-vehicle networks. So CAN bus is kind of the main character of the in-vehicle network technology world, right? CAN stands for Controller Area Network. It is the most commonly used in-vehicle network today by far, right? It is more or less standardized and mandated on most vehicles in the United States and Europe for diagnostic purposes. It was developed by Robert Bosch in 1991, is when the 2.0 standard came out, right? The most common nodes you'll find in the market today are actually 2.0B standard CAN bus nodes, and the 2.0B distinction is that they allow for the use of 29-bit arbitration identifiers. Arbitration is the process by which CAN messages have their priority established, and this is the process by which CAN bus actually handles collisions, right? Collisions are detected and then resolved instantaneously, or almost instantaneously, through the use of arbitration IDs. I don't think we're going to talk too much about the actual arbitration process today because that's slightly more in depth for CAN bus, but this is it's how CAN does its addressing is with arbitration IDs. But I'll just put this out here now. CAN bus runs in a bus architecture, and it's a multi-master serial communication. So anyone can send a message, and the arbitration identifier isn't really meant as a source address or a destination address. It just identifies what kind of data is in this packet, right? So if you slapped a sticker to a car saying, this car has oranges in it, right? That's kind of what that does. Saying this truck has oranges in it doesn't mean, it's specific oranges for one person. There's just oranges, and anyone that wants an orange can stop this truck and get an orange. That's a horrible example, but hopefully that'll get across the idea of what an arbitration ID does in a CAN frame, right? And then back to the CAN frames themselves. Each CAN bus frame in classical CAN can hold up to 8 bytes of data, right? So there are a couple different kinds of CANs. The most common CAN bus is high-speed CAN, also called dual wire CAN. And this is important because there is a single wire CAN that also exists, but dual wire CAN is the most common one. Uses differential signaling and commonly employs twisted pair cabling to add some EMI resistance to it, right? I mentioned that in-vehicle networks need to be reliable, they need to be robust, and this is because a vehicle is a pretty noisy environment. If you're not familiar with what EMI is, right, this EMI here, it's electromagnetic interference. This is when things like power supplies or radios or microwaves or anything that's giving off, radio waves, those radio waves can have, on a physical, physics electronics level, they can actually corrupt some of the data being carried by a guided medium if that guided medium isn't properly shielded, right? So this twisted pair cabling is also there to help that, because the way twisted pair cabling works, I'll explain that in a second. I have a slide where I like to go a little bit more in depth into that. But the differential signaling and the twisted pair cabling work together to help mitigate EMI impact, right? Speeds are theoretically up to 1 megabit per second, although in practice you're more likely to find 125 kilobits per second, 250 kilobits per second, and 500 kilobits per second speeds in most cars, right? 1 megabit speeds are heavily restricted by cable length, because at a certain length of cable, it's no longer practical to transmit that fast. And it's just usually a better idea to stick with 500 kilobits. It's more reliable, right? Just take my word for it. This is a quick look at what a CAN bus actually looks like from the physical perspective. CAN buses are usually terminated with 120 ohms on both ends, right? This is a high-speed CAN bus, by the way. And then on each end, each node will have its own CAN transceiver that is connected to a CAN low line and a CAN high line, right? So CAN bus is technically a dual wire system when we're talking about high-speed CAN, right? And these are intertwined like this. This is the twisted pair that I was talking about, right? So you can see that there's a high voltage CAN line and a low voltage CAN line, and the difference between these two CAN lines is what is read when a logic is being registered. That's the differential signaling. Excuse me. Pineapple juice is starting to make me burp a little bit. But anyway, back to differential signaling, as I was mentioning. So this is a very easy to understand diagram showing how differential signaling works in CAN, right? Here we have a logic graph and an actual physical voltage graph. Right? So in high-speed CAN high and CAN low both rest at around 2.5 volts. This is their kind of resting state, and this is what is read as a recessive logic or a logic 0, right? As counterintuitive as it might seem, logic 1 in CAN bus is considered recessive and logic 0 is considered dominant, right? So this shows here how the physical bus would look and the logic bus would look if we were to transmit 101 on a CAN bus, right? We'd have the recessive, right? Both lines here at 2.5 volts with a 0 volt differential. We have dominant for one, bit cycle. During that bit cycle time, right, the CAN high line gets driven to 3.5 volts and the CAN low line gets driven down to 1.5 volts, right? This 2 volt differential is what is kind of registered. It's what's recognized as a logic 0, right? And then the bus voltages go back down to 2.5 and another recessive logic 1 is registered. I'm going to talk a little bit about how the twisted pair cabling actually protects against EMI. Let me pull out my pen and PowerPoint. So twisted pair cabling means that the two bus lines, CAN high and CAN low, are intertwined with each other very tightly, right? They aren't just straight across, from one node to another. You can make them that way, but it's better not to because of EMI, right? So the way that works, because those cables are intertwined so tightly, any electromagnetic interference that hits that bus is very likely to hit both CAN high and CAN low, right? So what happens if that kind of scenario occurs? Well, let's draw it out. Say there's a electromagnetic pulse and it's CAN high and CAN low at the same time and causes a voltage spike that looks kind of like this, right? And then later down here, it also comes up like that, right? So that's the CAN high. I should have switched the colors here. I'm kind of a fool, but I didn't do it, so just forgive me, right? The idea is because they're twisted so tightly, we're likely to see the same exact behavior on CAN low, right? Now I'm doing a really shitty job of actually drawing this exactly the same from one to the other, but let's just pretend that these look exactly the same. And then while the bus is in the recessive state, so let's say that interference continues, right, we'll see the same physical impact on both bus lines, right? Now, why is that important, right? Remember how the differential signaling, the differential part means that we're measuring the voltage not based on the raw voltage values of the lines, but by the difference between the voltages. So here, when we're trying to transmit the 0, even though we have this interference, the difference between this point and this point is still 2 volts, right? So we'll still read a 0. The difference between this point and this point is still 2 volts, right? Even if this goes negative, right? And we have the same interference here because those wires are twisted together. The difference between this low point here and this low point here is still 2 volts, right? So the idea is by combining differential signaling with twisted pair, you have this very robust system where even if you bombard this cabling with electromagnetic radiation, you're still likely to get your message across because of the way CAN bus is set up. I think this is very clever, and it's one of my favorite things about CAN bus. So it's always good to talk about this and just appreciate the quality of engineering put into this technology. But onto less common types of CAN bus. There's single wire CAN. It is designated as Society Automotive Engineers Standard J2411. It's CAN for applications with incredibly low bandwidth requirements and not as much robustness requirements. And as the name would suggest, it uses only one wire as opposed to high-speed CAN's dual wire. But on that note, it uses 33 kilobits per second as its maximum data rate. So quite a bit slower than high-speed CAN, and it does not use differential signaling, so it's not as robust or resilient to EMI. And the way the signaling works in single wire CAN is more of a raw voltage value reading, right? So you have a much larger differential between the recessive value and the dominant value. So in single wire CAN, 0 volts is considered recessive and 4 volts is considered a dominant bit, right? Low speed fault tolerant CAN, the importance of introducing single wire CAN is so that you understand that low speed fault tolerant CAN exists as a way to increase the reliability of high speed CAN, right? Even if you thought high speed CAN was incredibly reliable and robust from the description I just gave of it, there's still more that can be done. So the way low speed fault tolerant CAN works is it does a couple of things. It actually divides the termination on the bus amongst the nodes, right? So if you remember let's just go back a second to the slide where I showed the high-speed CAN bus, right? You have 120 ohms here and 120 ohms here, right? These two 120 ohm resistors in parallel come out to be 60 ohms, right? But these become more or less single points of failure. You remove one of these and your bus doesn't work anymore. But in fault-tolerant CAN, right, low-speed fault-tolerant CAN, you distribute the resistors along the nodes on the bus to actually give the opportunity for the bus to keep working even if one of these nodes gets removed. Even if one of these resistors gets removed, you still have enough resistance on the bus for CAN bus to work properly, right? It also has higher voltage differentials to keep things from getting to it's just more robustness, just in case there's an especially large amount of EMI interference, right? CAN high gets driven to 5 volts and CAN low gets driven to 0 volts in the event of a dominant bit transmission, right? And then another fault tolerance feature included is that if a wire is damaged, then LSFT can actually switch over to single wire CAN operation, right? But at the cost of this is that it's more expensive to implement, and the maximum data rate you can get with this kind of implementation is only 125 kilobits per second. And for those reasons, it's not very commonly seen, but it does exist, and I figured I'd share knowledge of its existence with you guys today. So just to summarize, where CAN is used, right? Instrument clusters, component control, HVAC, so your car's climate control, etc., headlights, brake lights, window status, GPS, diagnostic information, so much more, right? GPS, I mean, like the CAN bus will carry GPS data to share with other parts of the vehicle. Your CAN bus isn't generating GPS data. You're getting that from a satellite, but you already knew that, right? So point is, CAN bus is truly the main character of in-vehicle network technologies. It has the most applications, and it is also, I would say, the easiest in-vehicle network technology to begin to learn how to use, because there are lots of open source, freely available software tools that you don't even need any hardware really to get started to learn how to use a CAN bus, right? They have visualization software available that you can use if you wanted to get started, but that's not what this talk is about. But it's truly the coolest in-vehicle network, I believe, and I don't think it's ever going to be phased out no matter what anyone tells you. But moving on, the next one we're going to talk about is LIN. LIN stands for Local Interconnect Network. It's kind of like CAN bus's little brother, right? It was actually created after CAN bus despite having much lower specs from a technical perspective, and it was made to take the place of CAN bus for low bandwidth applications that didn't require the same grade of reliability and robustness that CAN offered, right? Like CAN is pretty cheap as far as in-vehicle network technologies go, but you can always go cheaper, right? So for things like your, I'll say some examples later, but very low speed, very low bandwidth applications, LIN bus will usually do the trick, right? And it's also a uniform standard for improved compatibility across manufacturers. It runs on basic, you can actually program a basic UART transceiver to work with LIN, right? Utilizes a bus topology, and it's a broadcast serial network with a master-slave architecture. Supports up to 16 nodes, right? So it's much simpler in its design compared to CAN, but like I said, it has its place in the industry because sometimes you don't need any more than those very basic capabilities. So LIN also uses a single wire, similar to single wire CAN, and it only communicates at 20 kilobits per second. So it's even slower than single wired CAN, right? But it has guaranteed latency on its transmissions because it utilizes a scheduling table where the master will periodically pull slave nodes for their data, right? And it includes data checksum and error detection for basic error handling, right? As you'd expect of something used in automotive, right? It even has that bare minimum robustness included into it. And like I mentioned just previously, the transmission is done according to a scheduling table, and here I have a quick diagram showing how a transmission will go. So normally you'll have one device on the bus considered the master device, and that master has a schedule according to which it will send out this master header frame, which kind of includes, it'll essentially say like, hey, I want this data, right, according to this identifier. And then the corresponding slave node that has the data associated with that identifier will then fill in the rest of that data, right? The slave node will then begin to transmit from this point, right, after this response space. And on the bus, the way that messages appear is as one LIN message, but it's actually half transmitted by the master and half by the slave, right? So this is all part of a automated sequence where the master the master node will send out these requests periodically for data updates, and the slave nodes will respond in turn as they're pulled, right? So it's pretty simple, but it's pretty effective. You'll actually see LIN bus used in things like if you have powered seats in your car, right? The ability to relax your lumbar support, right? Kind of the motorized seat control, right, for comfort. That's usually done in LIN bus. Other things of very low importance, I'd say probably moving your mirrors, right, that might be dedicated to LIN bus. Anything that you can see as being not incredibly important in a real-time high-speed driving situation, there's a chance it could be dedicated to LIN bus. So it's always good to know that LIN bus exists, even if it is kind of a small-time player in the automotive sector. So talking about some of the bigger boys, the more newer in-vehicle network technologies, the more recent ones with higher specs, we get to FlexRay. It's high bandwidth, high reliability communication, and it's developed for applications where CAN isn't appropriate or fast enough, right? So FlexRay is kind of like a next-gen in-vehicle network. It uses 2 communication channels between each node, and it uses differential signaling like CAN, but it actually has 2 channels, an A and a B channel. So you have 4 wires per connection, right? So it adds redundancy, but it also makes it a pretty expensive protocol to implement, right? But that's kind of how it goes, right? If you want to add more speed, more functionality, you need to make things a little bit more expensive just because that's how the world works, right? FlexRay payloads support up to 254 bytes in size, and FlexRay is commonly used in X-by-wire systems, right? So because of its high speed, because of its robustness, in a similar vein to that of CAN bus, you're able to use it for things like direct control of throttle, direct control of steering, and direct control of braking, right? The theoretical maximum data rate is about 10 megabits per second, so about 10 times as much as CAN's theoretical maximum speed. But since it's a proprietary protocol, it is a little bit more expensive and also a little bit more complicated, especially for the car hacking crowd. It's not as easy to get tools that can work with FlexRay, especially if you're just starting and you don't have a a wealthy industry supporter providing you with industry grade tools, it can be hard to get involved with FlexRay just because of how complex it is, right? But moving on, starting to talk about another next gen in-vehicle network technology is CAN-FD. So CAN-FD, the FD stands for flexible data rate. It's the evolution, quote unquote, of traditional CAN bus, right? It retains many, if not all of the features of classic CAN, right? And this is, it was kept that way because of the success CAN had in the industry, right? It worked really well. We're still using it today, even though it's over 30 years old now, I think. Yeah, about 30 years old. But it does its job so well, there's no real reason to phase it out. But if you wanted to be able to add higher, if you wanted to be able to use CAN in applications where its basic data rate wasn't appropriate, you would need some kind of evolution for that. And CAN-FD is the manifestation of that desire, right? So the flexible data rate is achieved by increasing the rate of transfer of the data portion of a CAN message after the message arbitration has been completed, right? And this is just a reality of things, is due to some issues with classical CAN controllers. Some of them will flag CAN-FD messages as errors, so it has a bit of backwards compatibility issues. Sorry, I'm trying to talk a little bit faster than I should. I'll slow down a little bit. But CAN-FD payloads can range from 8 bytes of data to 64 bytes, and it can which means it transmits 64 bytes in the same time it takes classic CAN to transmit 8 bytes, right? So the theoretical maximum speed of CAN-FD is going to be about 8 megabits per second, but in reality, because you only speed up the data field portion of a CAN-FD message, the real-time practical throughput is about 6 times that of CAN bus. So about 6, maybe 7 megabits per second at absolute maximum, right? Because you have to keep the overhead and so on the same speed in order to keep cable lengths feasible cable lengths appropriate, and for backwards compatibility, especially if you have nodes that are equipped to experience CAN-FD messages but aren't really CAN-FD nodes themselves. There's kind of like a gray zone for that, right? But the maximum data rates, according to estimates, will vary. Some people will say it can go as high as 10 megabits, but less optimistic estimates settle around the 5 to 7 megabit marker. So moving on, MOST is the media-oriented systems transport. It's optimized for in-vehicle media systems, so it's very, very high speed. Uses a daisy chain topology, the ring topology that I showed earlier, right? And it uses a master device for timing that manages communications. And MOST is one of the first in-vehicle networks to support optical fiber physical layer, making it more or less impervious to electromagnetic interference. MOST has never been used for things like critical vehicle control, right? I mentioned that it's optimized for in-vehicle media systems, and that's why it has such a high frequency, right? High bandwidth, right? Because you need to be able to process things like video, process things like audio data, process anything that's going to be used by a media console is probably going to be very high quality data. If you want it to be, competitive in the market today, right? I'm kind of a quality buff myself when it comes to watching anything on a screen. But it comes in a couple of flavors, right? MOST 25, 50, and 150, right? Each of these corresponding to the actual speed, and each one of them has shown to be applicable to different physical mediums, right? To the best of my knowledge, MOST 25 was only implemented on fiber, and then 50 and 150 can be used on fiber or optical fiber or copper. And then it was also a candidate for implementation of Ethernet in automobiles, right? The way MOST was set up. But speaking of Ethernet, automotive Ethernet is kind of like the cool kid on the block, right? The new transfer student that everyone is interested in is automotive Ethernet, right? They're very dynamic, they're very high powered, and everyone is interested in seeing what they can do, right? It's almost traditional to Ethernet used in computers and traditional network infrastructure, but it uses a different physical layer, right? I believe it only uses 2 wires as opposed to most traditional Ethernet connections is 4 wires for data transfer, but don't quote me on that. I wouldn't call myself an automotive Ethernet expert per se, just because it's not actually found in that many cars yet, right? It's hard to do a lot of research on something that's not really in the industry yet. But unlike some of the other networks we talked about today, Ethernet is point-to-point, which makes it a little bit harder to scale to more nodes because you need to add a lot more hardware, right? But it has incredibly high bandwidth potential, which is especially attractive if you're talking about autonomous cars, fusing data from tons of different sensors and processing all of that data for real-time decision making on the road, right? But some more details about automotive Ethernet. Your traditional RJ45 connector isn't really appropriate for an automotive environment. It's not resistant enough to vibrations to stay connected without deteriorating very quickly. So there are a lot of different physical connectors that have been made by different vendors, but I wouldn't say there's an industry standard that's been established yet. But some of the more common ones include Broadcom's Broad R Reach type, right? That's a decently common automotive Ethernet connector type as far as connectors go. But anyway, about the important thing, the data rates, they can reach as high as 10 gigabits per second. I don't know why I wrote 10 G megabits per second here. That doesn't actually mean anything. Typo on my part, but please forgive my ignorance, I suppose. But it is an expensive technology to implement, especially with how new it is. And so there's a case to be made that you shouldn't always use Ethernet just because you can. And looking at this chart that shows a comparison of the different data rates, right? Ethernet is quite, easily winning the race, right? This is a logarithmic scale, so you can see we go from 1 to 10 to 100 all the way up to 1 million kilobits per second, right? These other technologies don't even compare to the speed Ethernet can put out. But at the end of the day, do you need this much speed for most of your applications? And the answer is no, right? Like, why don't we just use Ethernet for everything now that we've figured out how to use it? Isn't it just going to save in-vehicle networking, right? No more thinking about what technology to use, just use Ethernet. Well, no, right? It's expensive to implement. It's new to the automotive domain, so there's no proven use for it as the only in-vehicle network you need, right? And it requires more hardware thanks to the fact that you might need switching hardware in place to actually do the addressing, at a higher level, especially if you want to implement TCP or IP into your TCP/IP in your vehicle, which increases the point of failure relative to that one switch being a single point of failure for the entire network, so on and so forth, right? And the real important thing here at the end of the day is the cost argument. It's not necessary to have that much bandwidth all the time, right? The old saying, why use a fire hose where a squirt gun will suffice, right? It's truly a case of knowing how much data you need, how fast of a connection you need between these two ECUs. Is it really worth it to invest in an Ethernet implementation if that means you have to increase the processing power on each of those ECUs as well, right? Because CAN bus, for example, is much simpler to implement than Ethernet and doesn't require as much processing power on the ECUs, so you can use slightly lower grade ECUs for a CAN bus connection than you would for an Ethernet connection, right? There's a lot of reasons to choose a more optimal solution when it comes to lower bandwidth requirement applications, right? So that about wraps up my talk. I don't have any more cute diagrams or clever things to say, so thank you all for listening. I hope you were able to learn something about in-vehicle network technologies and how they're used in the automotive industry. My email address is listed below. You're welcome to send me an email if you have any questions. And yeah, hope you enjoyed the rest of the Car Hacking Village, and I will be signing off now. Thank you very much.
All right, Camille, thank you so much for what a nice presentation about in-vehicle networks. Who knew there were so many different types of networks going on inside your vehicle? Sounds a little complicated, right? All right, so we have around 15 minutes until the next talk. The next talk is going to be OBD and what can we do with it, so check it out. We'll see you here in about 15 minutes. right, boys and girls, ladies and gentlemen, we have our next talk at CHV101. The title of this talk is OBD, and what can we do with it? Infinite is going to give us this talk, and he's going to tell us a little bit about what OBD is and how we can play with this. How can we reverse engineer it? What does it mean? What is possible? So please help me introduce Infinite and his talk, OBD, and what can we do with it?
OBD, what can we do with it? OBD and CAN, a brief introduction. Who am I? Xavier D. Johnson, also known as Infinite on Twitter, born and raised in the Motor City, hacking since 12 years old, first mentor, organizer of DC 313, director of MySec Detroit, and show host at How They Got Hacked. I'm going to be talking to you today about the history of OBD, the standardization of OBD 1 and 2, what data we can get from OBD 2, the architecture of CAN and OBD 2, and what can we do with it all. So starting off with the history of OBD, where did we get it? Well, the development and usage of OBD goes back to 1960s, and there were several organizations that set this groundwork. CARB, otherwise known as California Air Resources Board, SAE, or the Society of Automotive Engineers, ISO, International Organization for Standardization, and the EPA, Environmental Protection Agency, all work together to develop OBD. OBD 1 and 2 standardization. OBD standardization in the US started in the late 1980s after the 1988 SAE recommendation that called for a standard connector and set of diagnostics. In 1991, the state of California required all vehicles to have some sort of basic onboard diagnostics. This is what we refer to as OBD1. 3 years later, in 1994, California mandated that all vehicles sold in the state starting in 1996 must have OBD as recommended by SAE. We now refer to this as OBD2. In 1996, OBD2 became the mandatory for all cars manufactured or sold in the United States. OBD standardization around the world. In 2001, eOBD, the European version of OBD, became mandatory for all gasoline vehicles in the European Union. By 2003, eOBD became mandatory for all diesel vehicles in the EU. And starting in 2008, all vehicles in the US were required to implement OBD2 through a controller area network, as specified by ISO 15765-4. What data is accessible from OBD2? OBD2 provides access to status information and diagnostic trouble codes, otherwise known as DTCs. These include powertrain, these things, engine and transmission, emission control systems, as well as the vehicle identification number, calibration identification number, ignition counter, emissions control systems counter. Let's dig into the architecture of OBD2 and CAN. So OBD2 is a port that's usually located in the footwell of the driver's side of a car. It's been mandated in cars since 1996. OBD2 standard itself defines both the electrical interface and messages, primarily the DTCs, created to be used as a standard way for vehicles of any manufacturer to allow independent repair shops and dealers to test for emissions. OBD2 is a 16-pin connector port. Although only 9 pins are mandated by the standard itself, most vehicles include an additional connectivity such as GM LAN or Chrysler CCD. They are used at the dealership, for example, to update software on the ECUs, to perform additional software testing, or to troubleshoot problems specific to that vehicle's make and model. Aftermarket OBD2. At first, only standard OBD2 connectors were able to read diagnostic information. Manufacturers have been able to, over the years, reverse engineer the communication architectures to enhance their own offerings. With the advent of inexpensive cellular, Wi-Fi, and Bluetooth components, Aftermarket OBD2 manufacturers have expanded their products to include entirely new classes of services, such as pay-by-the-mile insurance, vehicle use tracking, and commercial fleet management. So what can we do with this? Way more than transmitting DTC. CAN controls, or controller area network, controls hundreds, if not thousands of sensors and ECUs that control everything from operating the vehicle, steering, accelerating, braking, all the way to infotainment and locking the doors. All this information is being passed over the CAN bus. The CAN bus is nothing more than a TCP-based packet switching network. This is the same stuff that you see on your day-to-day jobs and most organizations' IT infrastructure. The CAN protocol sends all this data to all the nodes on each given bus, and each CAN frame includes a destination address. Now, how do we attack it? Well, OBD2 aftermarket devices can potentially retrieve CAN traffic from outside of the vehicle from something like a Wi-Fi connectivity and pass it through unfiltered internal CAN bus through OBD2 ports. So nodes inside of the CAN network on the CAN bus are expected to ignore traffic that's not addressed to them, but CAN frames don't have source addresses. So there's no way for you to be able to tell legit data from spoof data. This is where our journey begins as security researchers, and for us to be able to go and continue to reverse engineer these protocols to understand exactly what's happening over these CAN buses, for us to be able to use things such as OBD2, potentially leveraging connectivity that's being built into the vehicles, such as Wi-Fi or Bluetooth, for us to be able to utilize those connectivities and to leverage that to further attack. Thank you. And if you have any questions, please don't hesitate to reach out. My Twitter is infinite, and take care.
All right. Thank you, Infinite, for your talk about OBD and what can we do with it. If you guys have questions for Infinite, please go ahead. You can type your questions into the CHV101 support talk channel, and someone from the CHV will be able to respond to it. We got lots of experts on the line here. So, all right, here in about 40 minutes, we have our next talk scheduled. This is Fundamentals of Diagnostic Requests. Going to be really interesting. Robert Leali is going to give this talk, so looking forward to that. Come back in about 40 minutes and we will see you then. All right.
Hi everyone, my name is Michael. I go by CompuKid Mike, and this is the badge talk for the Car Hacking Village. The badge team consists of me and my wife. She does all the design and graphics work, basically all the pretty parts of the badge. I do the electrical side of it. These are some of the badges we've produced in the past. The Goonbox badge, the Sonic Screwdriver, and the little
All right, welcome back to CHV101. We have a small change in the plan today because it seems that we got a technical difficulty. So if you're tuning in for the diagnostic talk, this unfortunately is going to be rescheduled, or maybe we'll see how it works out. However, we've got the CHV badge talk. CompuKid Mike decided he'd jump in and take the time slot, so he's going to talk to us about the CHV badge this year. It's a really cool badge, so I'm really looking forward to his talk. And if you guys have any questions, just submit them in the CHV101 support text channel. And if you're watching us on YouTube or Twitch or wherever you might be watching us, you can join the conversation at discord.gg/defcon. All right. Well, without further ado, let's hear the talk from CompuKid Mike.
Hi everyone, my name is Michael. I go by CompuKid Mike, and this is the badge talk for the Car Hacking Village. Badge team consists of me and my wife. She does all the design and graphics work, basically all the pretty parts of the badge. I do the electrical side of it. These are some of the badges we've produced in the past. The Goonbox badge, the sonic screwdriver, and the little TARDIS. And then that was a couple years ago. Last year we did the bow ties and another sonic screwdriver, as well as the Fifth Element badge. This year, the car contacted us and asked us to do their badge. And so this is what we came up with. Lots of blinky lights, which is of course the most important part. And then this year the car hacking badge is an automotive Ethernet media converter. So, what is automotive Ethernet? It's similar to regular Ethernet, but it runs over a single twisted pair instead of 2 to 4 twisted pairs like regular Ethernet. Underneath, it's pretty much just a different PHY chip. Couple differences: it runs at a fixed speed, doesn't do auto negotiation, and then there are primary and secondary sides to the connection. So it's not universal like normal Ethernet, and it's made to handle an electrically noisy vehicle environment. So here's a little bit of the difference on the actual electrical interface for it. This is what's called generally referred to as magnetics for regular Ethernet connection. And then here for automotive Ethernet, you see it's very simplified. You have the choke here, a couple capacitors, and that's it. Now, when I say that's it, I don't really mean that. And we'll get into that a little bit later about how datasheets tend to leave things out or say the wrong thing. So, how to use the badge. Everyone who got a badge should have gotten this instruction sheet. So obviously USB connector, power switch here. Flip it to the top to run on batteries, bottom to run on USB. When you turn it on, it will be in one of the blinky modes. Press the mode button over here, cycle through those. There are 4 different ones. Once you get through those, it will go into the Ethernet modes. Now, when it's in those, only these bottom lights are going to turn on, and not all of them. So there are 4 different Ethernet modes, and as you click through them, you'll notice the left and right LEDs here on each side change. And so what that's doing is changing port 0 here, these 2 pins, and port 1, these 2, changing whether they are set as the primary or secondary side of that connection. So that's important for when you're connecting it to like an ECU in a car or a camera, other Ethernet peripheral. It matters if each side is set as primary or secondary. There needs to be one of each. If they're both sides are primary, they won't talk to each other. Same with secondary. And then the center LED here will tell you if that automotive Ethernet port is connected or not. So Port 0 here on the left, these two pins connect to this RJ45 jack over here, and then P1 over here to P3. And so there are two completely separate automotive Ethernet media converters. So maybe wondering, using some words that maybe might be weird. Media converter means it's simply converting between the two different physical versions of Ethernet here. So automotive Ethernet is just a different physical connection between devices. Behind it, the protocols are all the same as regular Ethernet. Same data goes across and everything. It just runs over this single twisted pair, and so it's a little bit different chips here. So the badge transparently converts between the two. If you wanted, you could even connect one computer in here, bridge these across between port 0 and port 1, and connect another computer here, and this badge will convert the Ethernet twice. From regular into automotive and then back. And so you can communicate through the badge that way. Not that that's super useful, but it can be done. So the board was designed in KiCad. And we also used Inkscape and CorelDRAW for the artwork, and a plugin called SVG2 Shenzhen. And that is an Inkscape plugin that makes board artwork for KiCad really, really nice, and it's an awesome tool. Here's the schematic for the board. This is on our GitHub. Link down here. And you'll notice this big NDA block in the middle. We'll get into that a little bit more later. But needless to say, NXP has put the automotive Ethernet chip info under NDA. Firmware was developed in NXP's MCU Espresso IDE. It works fairly well. It's an Eclipse-based IDE. It is cross-platform and it's free. As for the actual firmware, it's not open source at the moment. Again, NDA issues. We're trying to work with NXP on that and see what we can and can't release. So hopefully we'll have more info on that later. So, tools. We made a couple tools to do this badge. One of them was a testing jig. So one of the issues we run into is you got these big Ethernet jacks that go on it, and a battery holder, and once all that stuff is on there, it's very hard to fix any issues with the boards, any solder connections that are messed up, anything like that. And so this testing jig, all these little points are little spring-loaded pins, so that we can press the board down on here before all the big connectors are on it and test to make sure it works. And so we'll plug network cables into these and run them to a couple computers so we can talk back and forth to the badge and make sure everything's working right. Here on the bottom you can see all the connections down underneath. They're super ugly, but so one of the other tools we made was a depanelizer. So the boards come to us like this from the factory, and this is done so that we can run multiple boards through the pick-and-place machine and through the reflow oven simultaneously. It means less boards that we have to handle. Makes everything a little more efficient. But you have to cut the boards out of these panels. You can kind of bend the boards and break them out, but it's difficult, and you risk hurting the board. So I was looking for a good easy way to do this, and I came across this tool. This is made by Heiko. It's a manual little nipper, and it cuts those little tabs out. It works well, but it's hard on your hands. We made 250 of these badges. Each of them has 9 tabs to cut, so it's a lot of work. So I got looking around before I bought this tool, and looking for reviews, see if it's even going to work, if it's worth the money. They're not that expensive, about $25. And I came across a video by a YouTuber named Clow42, and he is awesome. He made a review of this tool about 6 months ago, I think. And so I was convinced. And then I got looking through his YouTube channel, and a few hours prior to me seeing that video, he had uploaded a new video of how he made a pneumatic powered version of this tool. And as part of that, he released the 3D printer files for it. And so I decided that was fate, and it needed to happen. So using his 3D printed design, I printed my own. And so this is a little pneumatic cylinder. It pulls on this rod and pulls the handle of the tool down. Just removed the rubber handles from it. And we've got a little foot switch that actuates it, and it is super nice. Really easy to use. It was a lifesaver during this project for how many boards we had to depanelize. All right, let's talk about when things go wrong, because they will. They always do. So we ran into quite a few issues with this project, but in the end we made it work. So NDAs. Like I said before, the automotive Ethernet chip is under NDA. I don't know why. There are other companies that make similar automotive Ethernet chips that are not under NDA. So not sure exactly why NXP decided to do that, but they did. So it took quite a while to get through the whole NDA process. But once we did, we got what we needed. One of the big issues was that the public data sheet, what you can get off of DigiKey and Mouser and all the other parts places, doesn't even include the pinout for the chip. You have to go through the NDA process to get that information. It also doesn't tell you what any of the registers in the chip are, so that you can control it, anything. All the datasheet tells you is kind of what it does and how big the chip is. So now, don't take this as me ragging on NXP. They're an awesome company. In fact, they sponsored the badge and provided the automotive Ethernet chips and the main microcontroller on the board. So kudos to them. That was awesome of them to do. But NDAs are still a pain. Okay. Next thing we ran into is that datasheets lie. So this is from the TJA 1100 datasheet. This is not from the NDA one. However, the exact same diagram is in the NDA datasheet. And you can see this is the physical connection for the automotive Ethernet. You can see the choke and the capacitors like before. I mentioned before, that's not all. So there's this section here, and this nice little note that says that it is optional. Now, when you're making badges, you're building them to a price point. Right? You're trying to make them cheap enough for everyone to afford it, and you're trying to make it simpler because you got to assemble and test all these, and more parts makes it harder. And so if a datasheet says something's optional, I'm likely going to leave it off, right? Because these are not devices that we are taking to market, that we are going through FCC, all the EMC testing and all that. So we left it off on the prototype. That was a mistake. That is not optional. And if you go into this application hint thing, it's got the same diagram, but without the optional note there. So it is very much required. It doesn't work without it. So that was super frustrating. Trying to get the prototypes to work before we realized that was the problem. The next one, datasheets sometimes hide important info. So this is for the main microcontroller, and this pin, along with a few others that are like it. So it's got information about it, and the different things that pin can do, and every one of them says general purpose digital input-output pin, and every one of them has a little footnote number here. As I was going through this, didn't notice that this footnote number is different than the rest of the pins. That this is a true open drain pin, which means that it cannot output voltage. It can only connect the pin to ground. That's a problem when you're trying to drive LEDs. So the frustrating when it says right here that it is a general purpose digital input-output pin. That's not true. Next thing we ran into was default KiCad libraries. So, when you're, making up your schematic and everything, it's nice when there are pre-made libraries like this, right? It looks pretty. It's got all the good stuff on there. It's got all the right pins. Perfect. So put that in there, right? It's got pins R1 through 6, the LEDs. It's great. Only it didn't work. And so after much troubleshooting, I finally got looking at this closer and realized it goes 1, 4, 2, 3, 5, 6, when what I was expecting was 1 through 6. And so 4 of the pins were connected to the wrong pins. So the prototypes have some very nasty bodge wires on them to get that to work. So don't always trust the KiCad built-in libraries. Some of them have things like this. And so you can see I changed it to the proper part number and made my, copied that library, edited it to make it the right pin numbers. And it works on the end boards. All right, part availability. So whenever I'm going through doing design for a badge, one of the big things is always make sure that whatever part you're choosing, there's a lot of them in stock, because it sucks when there's not. And so, like normal, I did, and everything was great, and there were tons of them. And then when we went to order the final production run, the RJ45 jacks, there were only 115 of them in stock anywhere. DigiKey, Mauser, everywhere. Luckily, Mauser had already put in an order from the factory to get more of those, and they got to us on the 24th of July. So it was in time, barely. Got them so we could put them on the boards. The battery holders were a different story. They were completely out of stock everywhere, and not estimated to be back in stock until late August, early September, which was not going to work. Keep in mind, at this point, we'd already ordered all the boards and everything, so there was no going back. So I looked on Octopart, which is a really awesome site that lets you put in a part number, and they will show you all the different places that sell it and how much it costs. And so for the battery holder, we went through and scrolled down the list, and there happened to be one random vendor that had a few hundred of them. And I believe they were more expensive than DigiKey or Mauser were, but they had them, and we got them, and they worked fine. We got them on time, so that was a win. All right, manufacturing mistakes. So our production run of blank circuit board or bare circuit boards arrived on July 16th. Right? Like, awesome. We've got a few weeks to assemble these and get them out. Maybe we can even ship them a little bit early, and it'll be awesome. Except when I opened the box, they had done white silkscreen on the boards instead of black, like I had ordered. So, to the board manufacturer's credit, they did remake them at no cost, which I'm sure was terrible for them because boards are expensive, especially shipping from China is crazy expensive. But they remade them. It took 2 weeks, and we got the new boards on July 29th. So from the moment we got them, we started assembling, testing. We got them all 250 shipped out in 5 days. It was a crazy, crazy week and weekend. But we got it done. And in the end, we made awesome badges, and I really hope everyone likes them. If you have any questions, we'll be on Discord chat. Hit me up, CompuKid Mike, and thanks.
Awesome, CompuKid Mike. Thank you so much. And what a wonderful badge as well. Really cool. If you were able to get one before they all sold out, kudos, because that is awesome. And what a great thing with automotive Ethernet on board. You can really play with it. So awesome, awesome badge. All right. If you do have questions, you can go ahead and put them into the CHV101 support text channel, and We will answer them as fast as we can. The next talk we have coming up is cluster fuzz. So Mr. Ian Tabor is going to take us through fuzzing clusters or not head units, but dashboards and stuff like this. So really interesting talk. It starts here in about 40 minutes. So check back with us in about 40 minutes for the next talk with MintyNet or Ian Tabor. Title is Cluster Fuzz. All right, welcome back to Car Hacking Village 101. Took me a minute, but I had to get the right screen up there. The next talk is Cluster Fuzz with MintyNet. This is a very seasoned veteran of the hacking world. He's going to talk to us about fuzzing clusters. Now, what the hell is that? Well, he'll tell you. So if you guys have questions during the talk, please go ahead. You can add these directly into the CHV101 support text channel, and we will answer them after the talk. If you are joining us from YouTube or Twitch or wherever this is streaming to, please feel free to join the Discord channel, discord.gg/defcon, and join the conversation. So, without further ado, I would like to introduce MintyNet and his talk, Cluster Fuzz.
Good morning, good afternoon, good evening, depending on which time zone you're in. I'm Ian Tabor, or at MintyNet. This is my talk for Car Hacking Village 101, Cluster Fuzz, starting out car hacking on the cheap. First things first, who am I? You could say I'm the ultimate car hacker. I built this kit car 15 years ago now. It's based on a mid-1990s rear-wheel drive Ford running gear. However, it has a Ford Focus engine from around 2004. Doesn't weigh a lot, has quite a bit of power. It goes like stink, great fun to drive. It's not that complex vehicle. It only has 3 ECUs, 2 of which I built myself, both of which torque can. So you could potentially hack this vehicle. Please don't. It's great fun when it's driving. It's not fun when it's not. There's a little disclaimer down the bottom there. Car hacking is done at your own risk. If you brick your own car, please do not blame me or the Car Hacking Village. So onto my car hacking credentials. In 2007, I hacked my own vehicle, found an issue in the head unit in which you could get access to personal information inside the head unit quite easily. I disclosed that information to the manufacturer itself. I then did a talk about it at DEFCON group in London, DC 4420, B-side London Rookie Track, and DEFCON 26 Car Hacking Village. In 2018, I was also invited to be one of 12 security researchers to go to BugCrowd's live car hacking event. I then returned in 2019 to be one of 20 security researchers to go to the same event for the same manufacturer, but at their factory over in the US. Last year at DEFCON 27, I was part of a BugCrowd car hacking panel with Cybergiddens and Spectres, hosted by Chloe. I was also asked last year to go to the Auto Isaac Summit in Texas at Toyota's plant, where me and a couple of others were part of a car hacking vulnerability disclosure policy panel for HackerOne. I also, now for my sins, run the Car Hacking Village in the UK. I have my car in the box, PD0, which is all the electronics from a Peugeot 208 in a box in quite a portable form. Not as portable as being globally movable, but last year I did about 13 events, one of which was in Europe. I have been asked to take it all the way around the world: India, Australia, Brazil, America, Egypt. The only continent I don't think I've been asked to go to is Antarctica. This year I was meant to do B-side Stuttgart, B-side Brussels, but things have happened, as we know, and there's been quite a few virtual conferences, which also means my car in the box will be available for the virtual.carhackingvillage.com CTF. If you look for PD0, there is 2 Raspberry Pis attached, one on 2 of the buses, one on the 3rd. You can then basically hack that vehicle in a safe manner. You won't break anything really unless you try really, really hard. It's quite good that it's actually going to be used at DEF CON without me leaving my own home. I will miss the people. However, travel is not really fun at the moment. So there are some hints and tips for the CTF for the Car Hacking Village 101 in this presentation, and the fuzzing that I will show you. You may want to pause and rewind some of this at a later time, but I'm not going to give you any more hints than that. So where do we start? The assumption is you all know what CAN is, Controller Area Network. It's a differential signaling communication system that allows lots of devices on a single bus to communicate, and has an arbitration system to allow the most important message to go out first. You don't really need to know much more about that, but if you want to have a read, Car Hacker's Handbook by Craig Smith is a good read. So first things first, you need a cheap CAN adapter. I will go into those in a second. Once you have a cheap CAN adapter, you could try reading your own car. Be very careful if you do. I plugged in one of my own home-built CAN adapters into my 2017 Jaguar XE and managed to make the car lose its gearbox. Yeah, that was one of those moments where thinking, oops, I probably shouldn't have done that. And I was thinking pound signs. I did manage to get it back eventually, but it involves disconnecting the power for a considerable length of time, about 20 minutes, plugging it back in. All the messages were then reset. However, the next morning when I went to drive it, it took about 3.5 weeks to learn how to change gear again, because it had the automatic ZF gearbox from as used in a lot of automatic vehicles these days. So slightly easier and slightly less dangerous is testing something that you can actually use outside of the vehicle. Do not test on your own vehicle, because if you break your own car and can't get Johnny to school in the morning, your missus will kill you and you will be doing the walk of shame in the rain. Not a good idea. So I'm going to show you an instrument cluster that I have. I will show you how to interpret a wiring diagram, what then is required for power supply, and then some tools that you can use. And I will show you some fuzzing, and you can see some results on the screen of what's actually happening. So first things first is the NanoCAN adapter. I use this device as the PCB itself as my business card. I started doing it in early 2018 when I first started the Car Hacking Village, in that it was something I could give away at the conference to say, here's a way to start doing car hacking. All you need is $5–10 worth of components, which include an Arduino Nano, an MCP2515 module, bit of wire, the PCB, and the OBD2 plug as shown there. What you would then do is solder it all together as shown on the GitHub instructions. You then can program the Arduino Nano with a basic sketch that reads all messages, and you get an output like this. You can reprogram it with other sketches that allow you to read and write data, but unless you know what you're doing, have a play with something first, listening and not sending. Here is the same output, but using PuTTY to interpret the data instead of the Arduino IDE. Again, if anyone wants one of these PCBs, hit me up on Slack or on Twitter, or email me if you want to. I will put it in the post. If you're a distance away, it might cost you the postage, which isn't that expensive. However, at the moment, postage around the world is getting silly because of COVID costing extra money. But hit me up anyway. I will be online after this talk on the Discord channels for questions, etc. Here's a second one of my adapters that I built. That is a pound coin 4 scale. That little device there is based on an ATtiny 1614 processor, which costs about 50 pence or about 50 cents, maybe a little bit less if you buy quantity. It uses the same MCP2515 CAN controller and a SN65 HVD230 CAN transceiver from Texas Instruments. The other two are from Microchip. And this will allow you to build a CAN device for probably less than $3 for all the components there. However, you need some extra parts to actually connect it to the vehicle if you want to connect it to the vehicle. There are two versions of this board. The red board is the main brains. The other board behind it, the little blue board you can see there, has the power supply and the connectivity onto the CAN bus. This one here is for nefarious purposes in that you can program the board at the top to listen for certain messages. When it sees a certain message, it can then start sending messages back onto the bus. This is powered from the CAN bus port. The blue PCB in the middle has the power supply that brings it down from 12 volts to 3.3, and the plug at the back will then go into the CAN OBD2 port and allow you to do various things. Be careful when you're doing this. Again, you could break things unless you know what you're doing. The other version of the tiny CAN adapter is here. This is a green board in the middle. This green board has an extra connector for a USB to TTL adapter. This adapter allows you to connect it to a Linux system using SLCAN, so serial line CAN and socket CAN and CAN utils. You can then send messages from the Linux system using CAN utils, which I will go into in a second. This again, all of the hardware there is probably about $7 worth of hardware. At some point in the future, I will put this up on GitHub as another repository. If you want me to, just pester me, I'll do it quicker. Another cheaper CAN adapter you can use if you've got a Raspberry Pi lying around doing not a lot. Here is the Pi CAN for Raspberry Pi. This is made by SK Pang in the UK. It uses the similar Microchip CAN transceiver and CAN controller. However, it's got a DB9 adapter to connect it to the CAN OBD2 port on the vehicle. You can also use the screw terminals. One little hint is just behind the DB9 connector are some solder pads. You have to solder them in such a way that it uses the correct pins, because there are two different versions of the same cable that may or may not work. Took me a while to work that one out, but this will cost you probably about $35 to $40, 35 to 40 UK pounds. The website there is in the UK, but I believe he sells them in the US as well through other outlets. Here again is a screenshot of CAN dump showing CAN messages from the CAN bus. Finally, out of the cheaper end of the CAN adapters is the CANtact, which is by Eric Evanchek, linked down the bottom there. This, I believe, is based on an STM32 and inbuilt CAN controller and CAN transceiver. This has got the same 9-pin adapter on the end, but a large USB-B connector. These retail, I believe, around $75, which is okay if you're in America, but if you're in the UK, you get stuck with customs and VAT. The jumpers in the middle there are for changing which pins go to where, slightly similar to the Pi CAN. He's currently on Kickstarter though, doing the CANtact Pro, which uses a slightly different processor but gives you two isolated CAN FD channels. Worth a look if you're interested in backing a Kickstarter. I might end up backing it myself if I haven't already done by then, by the time this goes out. So on to the instrument cluster itself. Here is the instrument cluster. It came from a Citroen DS3. They are not sold in the US. None of Citroen's group vehicles are sold in the US. This cost me about £30. which is probably about $25-ish. You can get these from eBay, at the scrapyard yourself, vehicle dismantler, recycler, etc. This one has a OBD2 port underneath in the middle there. This is because I use it for training purposes. So this is a very similar instrument cluster with regard to messages as my car in the box. Little hint here, listen up. The car in the box is based on a Peugeot 208, which is a similar size vehicle to a DS3. However, it's just got a slightly different cluster. The message structures are very similar, if not the same. Here's the back of the instrument cluster. As you can see, there's some screw holes which hold it into the vehicle, one of which screw holes is blocked up with a barrel jack socket. You've then got a 18-pin connector for the device. If you are purchasing it from a vehicle recycler or scrapyard, see if you can get the cable as well, because it's always easier to attach something to a cable that goes in specifically to that device, as opposed to using DuPont cables and trying to try and select the right cable. Just zoom in on the plug itself. It's 18 pins. Pin 1 is bottom right, pin 9 is top right, pin 10 is bottom left, pin 18 is top left, and as you can see there, pin 8 is can high, pin 9 is can low, pin 15 is 12 volts, and pin 18 is ground. Some of the other pins do things, some of the other pins do not, but be careful because you may break things if you send the wrong voltage up the wrong pin. So how do you work out what pin does what? You have to get the wiring diagram. This is the wiring diagram for the DS3 for the head unit and infotainment system. And if you zoom in right in the middle of there is the device that is the instrument cluster. As you can see, it has a little microprocessor and a couple of dials. That basically shows you what's inside it. It means it's got some brains, and it is the cluster. There is a key that tells you 0004 is an instrument cluster. However, it might be called something else, as in the language that it was originally written in, so in French. Looking at the wiring, it says 18V, which means it's 18 pins. BA means the color of the plug, which I believe is white. I can't remember. I may be wrong, but pin 18 or green is ground. Pin yellow is switched live. Pins 8 and 9 are can high and can low. It's sort of potluck on that one. You might get it right first time, you might not. But if you don't get any messages back out of the device, swap them over, see what happens. So power supply. This power supply here came from Amazon. It's a USB to 12 volt barrel jack. So USB at 5 volts at one end. It's got a boost converter in the middle. That then can step it up to the 12 volts that is required for the cluster. Technically, you need 13 point something volts if it was running with the alternator at full chat, but 12 volts should be enough. You could potentially use an ATX power supply, but I think it's overkill to have something that could potentially put 40 amps through it. So this is slightly safer. So on to Linux software. When using CAN under Linux, you need the package that is called CANutils. If you're running on a Raspberry Pi, apt-get install CANutils. It will then install all these components here. CAN dump will basically output all CAN messages from the bus that is currently coming off the CAN bus. CAN sniffer shows all messages that are changing on the bus. It does not show by default any message that is static. It will remove them from the screen, so it only shows you stuff that's changing. You can then make it highlight things to show when things change and when things don't. You can make it show all messages, but it's just one of the options. Can send allows sending of a single can message. If you're very good at shell scripting, you may be able to use that to send multiple messages in a for loop. It's not that easy to do unless you're really shit hot at doing bash scripts. CanGen is a slightly better version of the same thing in that it can generate messages either randomly or with specified logic. Finally, the last part is CanPlayer. Basically, this will replay messages that you have logged to a text file using CanDump. Excuse me. And then you can then record something on a vehicle, bring it back to your cluster, and then replay it and see what happens. And then by selectively grepping those messages, you could replay it and find out which message does the speed, which message does whatever, or just fuzz it and see what happens. So, shall we start fuzzing now?
Well, I think we have a little bit of a technical difficulty with MintyNet's microphone right now. We will try and fix it and get this working. He's going to join the channel again, so unfortunately, Minty, it's not working correctly. Sounds a little robotic, like a little schoolgirl robot or something like that. No, I'm very sorry. I mean, it's very amusing when you talk, but unfortunately, I don't think it's understandable for the listeners in the group here. All right. Well, I think log off, log on again. I will try and explain what's going on here. Or maybe we can do this also later as well once you get your microphone fixed. Minty, you want to try talking again? Of course, that's much better.
Absolutely nuts. This may or may not be a tip for the CTF. You may want to write that one down. So you can do it slightly slower, and you get a slightly less erratic movement of the dials. One thing I would do is not fuzz the dials from your own vehicle, because if you clock the odometer, when you put the dials back in your vehicle, it will change the mileage on your vehicle, because the one with the highest mileage always wins. So if you're on a limited mileage policy where you rent your car for a couple of years and you take it back and it's got 100,000 more miles on, they will charge you the difference. So be very careful. There I was just sending OB6 as a single message. You see it twitches slightly and basically then returns back to 0 because you're not keeping the message in play to actually send, keep the data changing. If you look, the first actual 11 bits of OB6 is the rev counter, 11 bits being 8,000 in decimal, which is probably about right for this kind of engine. The third byte there, counting from 1, actually controls the speed. By the way, they're hints for the CTF. But the good thing with the cluster is you can do cause and effect. So you can basically work through every one of those 2048 messages and run every single bit if you really want to. Don't count from 1 to 2 to the power of 64 because you'll be there forever. But if you jump through the bits 1 bit at a time, so as if you're doing 1, 2, 4, 8, 16, 32, you can actually see what bits do what to the display. Let me just see what we're doing now. Length of 8. That's just random data. That's just any old random data. And you'll see every now and then it might go to sleep. Every now and then some of the error lights might flash up. It's just whether you hit the right light, right message for the right light. Again, don't try this on a real vehicle because you can cause issues. There you go. There's another one. It now thinks it's in 6th gear. Now it thinks it's completely off. And now the odometer is showing 999,999. Not what you want to see on your car unless you're actually going for the 1,000,000 miles. So now I'm going to try and change the message to OF6. I think OF6 does the odometer. Again, slight hint there. I can't remember what bytes do what, but it's currently showing 999,999. Probably in kilometers because it's French and the values are actually stored in the cluster in kilometers. Here, if you do -DI, it increments and counts through the bit values. So it's going 1, 2, 3, 4, all the way up to very long way through. I think I'll cancel it in a second. But on some of the values, you may just see your rev counter jump up slowly. Again, 128 is quite an interesting one. You can get it to do disco mode. 128, I think, is for all your error messages. So some of those are 1s to make the light come on. Some of those are 1s to make the light go off, because some of the messages actually turn lights off. If there was an error condition, basically, if there was a cut in the cable, an error light would come on by default. So you have to send out a message to turn that message off. But it's always fun doing that. I have got one of my little tiny can adapters programmed for disco mode so that when it gets to a certain speed, it will actually do this on the dashboard until you then return the car back to 0 miles an hour, and then it resets and then turns itself off. You'd never be able to find it if you actually took it into a garage. Again, I'm just randomly fuzzing random data on random arbitration IDs. Actually, incrementing arbitration IDs. So that's sending all zeros, counting through every ID from 000 up to 7FF. One of them's turned this cluster off, and sometimes you'll actually get to the point of it won't actually turn itself back on until we pull the power. So again, be careful if you even think about doing this to your own car. Now, I think I'm going to try and do it with slightly different data, see whether anything changes. There we got a couple of error messages or lights flashing up because we were in the right bit, in the right message, in the right time. Some messages have to be sent at a certain frequency. The Discord channel, or hit me up in a call, Slack, or Twitter. I'd like to say thank you for everyone listening. Please don't break your own car, but give me a shout if you want a NanoCam PCB. That's me done for the day, so thank you very much. Again, I apologise for the audio both times. These things are sent to try us.
No problem. Well, I definitely want a Minty Net adapter. So how do I get one? Do I need to send you an email?
Just DM me with your address and I'll stick it in the post.
Great.
And I'll send a couple of stickers over as well. For the Car Hacking Village UK stuff as well. Again, I send them out as my business card. If you cover my post, I will send it global. Europe's slightly cheaper. So
actually, I remember the first time that I met you and you handed me a PCB and I was like, who is this guy just giving out PCBs?
That's my business card, which is the same adapter. I've got some slightly newer ones and I've got some slightly different ones because I've had to build them for other events. I made one for Black Hat Europe last year. I made one for B-Side Scotland because the B-Side Scotland badge was actually a CAN adapter because the Car Hacking Village was present. So you could come and find me, get the parts, build your own badge, and then come and play with the car on a device that you actually built yourself.
Very cool.
It's quite interesting having the car in the box at a conference virtually, because normally when I take it to a conference in real life, people come in, they look at it, they play with a couple of buttons and they wander off because they don't normally bring their laptop with them to a conference and they wouldn't necessarily have the right tools to actually interface with a car. Whereas now we're providing you with the tools and you've actually got a it's just a web browser between you and playing around with the car, and you can do whatever you want. In theory, had someone earlier scare the living life out of me by setting off the windscreen washers on my car in the box. Luckily, it wasn't attached to the bottle of whiskey at the time. Otherwise, I'd have had to drink it.
That's not so bad. But how are things going over there in the virtual car hacking village? I guess having a lot
it's been quite busy. There's been some people playing around. People don't like asking for help, so you see them struggling, and you send them a message, and then they'll be like, "Oh, yeah, okay, cool. That's cool if you show us what's going on." You get the odd person that's basically having a look around the system that's actually connecting them to the car. It's like, stop it. You're there to play with the car, not try and break my Raspberry Pi. But hackers are hackers, so needs must.
Yeah.
I have security in place for a reason. But if you want to break it, you're only spoiling it for the rest of them.
Well, for the guys that are listening, maybe they don't know about this, but we do have... so Ian's setup here, PD0, what is it?
Yep. P for Peugeot, D0 is 208 in hex because it's a Peugeot 208. You don't get Peugeots in America. For those in Europe, for those in not in Europe, it's a small sort of Fiesta-sized vehicle. PD0 has most of the electronics from the vehicle, and it actually thinks it's a working operational car. The only ECU it doesn't have is the the airbag ECU. For reasons of I don't really want an explosion going off in the middle of a conference and have to fill a form in, because we all know what the health and safety Nazis are like. But it actually thinks it's a working car, so there is a device attached to the crank and cam sensors to simulate the engine going round. There is a device attached to the ABS wheel speed sensors to simulate the wheels going round, so I can vary the speed on the vehicle. There are a couple of potentiometers for the fuel gauge and temperature sensor for the water. And then there's a couple of O2 simulators using a 555 timer to simulate the lambda sensor on a vehicle. You also have to have a couple of massive, great big resistors with them for the heater circuit. But I always tell the story of it gets very, very hot, these massive resistors. And then someone comes along later, touches them and goes, yep, owie. It's like, I told you not to touch them for a reason. There is also on the board a board that shows all the lights from the outside of the vehicle. So you can interact with any of the switches on the vehicle, make the lights go on, make the lights go off. The stereo works. The stereo actually has the same vulnerability I found in my DS5 in 2017, in that you can connect to it over Wi-Fi and then get access to the head unit over port 23, which is great. Once you're in, you've got full access to the file system, and you can get access to personal information like where you've been, your phone book, and your telephone history. Wonderful. Manufacturer didn't think it was that big of a problem until I pointed out the fact that the French president has a vehicle of similar make, and they went, "Ooh, that's not a good idea." Never know. But yeah, it's been fun. The only problem with it is I'm in Europe and time zones. Oh my god, I've got jet lag even though I'm at home.
Well, I can relate there.
You can relate to that. You're 1 hour ahead of me.
That's right. So I'm actually located in Germany and broadcasting all the way back to Las Vegas. So, Ian, what's the next steps for PD0? So are you going to do a new vehicle or what's up?
I've actually just recently put a reversing camera attached to the head unit, and that actually works. And I'm in the process of putting in the rear parking sensors for it, but I need to upgrade my software that runs the diagnostic system. However, the company I started work for recently may want me to build a new car in the box for them as part of their sort of showcase on what we can do as a company. Hopefully it'll be slightly more advanced than a small sort of town car Fiesta type size thing. Hopefully it'll be something of the German ilk, because they have a lot more tech in them and a lot more ECUs, which will be fun, trying to shoehorn 50, 100 ECUs into a box as opposed to my current box that has, I think, 13 ECUs in. But hopefully it doesn't have to be quite as portable, in that my current car in a box will actually fold down and go in the boot of my vehicle. The one I plan on mating may be slightly bigger. If you've seen it, for Virtual Car Hacking Village, there's actually 3PO by Grimm. That is also online. It's a 2012 Ford Focus. All of the electronics from the above. However, it doesn't think it's a working car. So I've got one up on them. But that was my inspiration in the first place.
Yeah. Well, both what Grim and you have done is really nice and great to see as a demonstration. So I really appreciate that.
Yep.
Thank you very much for the talk. Is there anything else you'd like to say before we close for today?
My car in a box will be around for the next 4 or 5 hours. No, not 4 or 5 hours. I'm in the wrong time zone. 3-4 hours, I think. It will also be around tomorrow during the opening hours times. It may be around slightly earlier because I'm in London and not Vegas, so I might be up early. But if you have any issues, just direct message me on Discord and I will get back to you and help you through any problems. If you really get stuck on the CTF, ask and I will show you how to do it. Yes, it's a competition, but if you're really stuck, there's nothing wrong with asking. I have no problem with giving answers out if you're nice about it. But yes,
that's the fashion, the style of Car Hacking Village. We're here to learn. We're also here to compete, but we're also trying to understand how things work. So
it's all about giving back to others. You get quite a lot in the car hacking space that are quite elitist. I think you know who I'm talking about. In that it's not a car hack unless you've got full remote control of the vehicle. Sorry, but car hacking's been around since computers ever came into a vehicle. Once upon a time, a car hack would be change the carburetor from a small carb to a big carb, get more fuel in, get more air in, make it go quicker. Just that now it's done with a laptop and not done with a spanner. So that's one reason why I like my kit car. It's basically bare basics. It has no brake servo, has no ABS, has no computers other than the engine ECU and my little data logger that I built myself. And your ass is 2 inches off the ground, and it's just great fun driving it. I think I know what I'm gonna do next weekend. After this weekend's fun at DEF CON. But yes. Again, thank you for your time, everyone. And if anyone has any questions, problems, or anything, just say hello. I won't bite much.
Well, that's Minty Net. Minty is one of the experts, so please ping him. Ask him questions. He's a great resource to have. If you don't know where to find something, resources or recommendations, just ping him. He's more than happy to help you. So thank you very much.
I also know some very, very clever people in other areas of car hacking. So I know a couple of people that broke the Teslas numerous times. They're quite handy to know.
All right.
Anyway, cheers, Mikey.
Yep. Thank you very much. And guys, we have the next talk coming up in around 17 minutes. So in 17 minutes, we're going to be talking about a little bit different interface. And this is something that is Bluetooth related. So we're going to be talking about Bluetooth security in automotive. We have Camille. He's going to give us this talk. So really interesting. And actually he goes through demos and everything like that. He's really hands-on. So join us here in about 17 minutes for the next talk, Bluetooth security in automotive with Camille Bendel. All right, welcome back to CHV101. We have a really cool talk coming up. This is Camille Gali. He's going to talk about Bluetooth security in automotive. To be honest, this is really cool. He loves to go into demonstrations and show everybody how it works. So really excited for this. If you have any questions during the talk or after the talk, please go ahead, write your questions into the CHV 101 support text channel at the Discord. If you're watching from Twitch or YouTube or maybe some other channel, go ahead, come over to the DEF CON Discord channel, discord.gg/DEF CON. We are in the car hacking village. Come join us, talk to us about car hacking. We'd love to have you. So without further ado, I'd like to introduce Camille Gali and his talk and presentation on Bluetooth security in automotive.
Yes, okay. Thank you for the kind introduction, John. Hello, DEF CON crowd, Car Hacking Village crowd, anyone after the fact, if you happen to be watching this sometime in the future. My name is Kamel. Today I'm going to be talking to you guys about Bluetooth in automotive. So, quick introduction for myself. This is just to make sure you believe that I'm qualified to be talking about the things I'm speaking about. So I'm an automotive cybersecurity technology architect at Whitemotion. Whitemotion is a very small subsidiary of Marelli, the former Italian automotive OEM Magneti Marelli. They merged with a Japanese automotive supplier called Calsonic Kansei a few years ago. And since at the time Whitemotion was a subsidiary of Calsonic Kansei, we're now fully owned by Marelli Corporation. I'm based in Tokyo in Japan. I'm trilingual. I speak English, Arabic, and Japanese. I've been involved in the automotive cybersecurity industry for about 3 years now. I've been on all sides of the table, including private consultant, trainer, red team, blue teamer, so on and so forth. I've worn a lot of hats in the last few years because auto cyber is a very new and expanding field, and no one's job is as well defined as they might like to think it is. I got involved in the community side of things a while back. I was an administrator on the ASRG board in Detroit, and I started the ASRG chapter here in Japan. ASRG, by the way, stands for Automotive Security Research Group. It's a group that is, I believe we're sponsoring the Car Hacking 101 this year at DEF CON, so we're kind of managing things through that. But yeah, it's a group dedicated to sharing automotive security resources and information, and helping expand awareness for the industry and help grow it as not only an industry for work and stuff, but also as a community. Right. So I consider myself a jack of some trades and a master of none. I'm not especially good at anything that I do, I like to think, but I have a lot of interests. So lately I've been doing a lot of Bluetooth stuff. Bluetooth has kind of become my pet project, right? Studying Bluetooth vulnerabilities and techniques for car hacking as it relates to what I do at work, as well as things like RF, digital forensics, and USB. My other hobbies are listed down there, and they're not incredibly interesting. But the picture in the background, you might be able to see. This is me, and this was my team for the 2019 Car Hacking Village CTF. So my team actually came in first place. We're Team Canucks. We're the best, and no one is better than us. And I think it's just worth saying, right? just more for the qualification. But anyway, enough about me, enough of that boring stuff. Let's get into the actual presentation. So, what is Bluetooth? Bluetooth is a very common cable replacement technology. It's found in virtually all smartphones, all computers, and a lot of the wireless IoT devices worldwide use Bluetooth as their main mode of communication, right? It operates in the 2.4 gigahertz frequency range, which is the same as some of the Wi-Fi standards, right? The 802.11 standards. And as a result, there's a lot of Wi-Fi chips that are bundled together with like a Bluetooth chip, right? So some manufacturers that make both Wi-Fi and Bluetooth hardware, they'll actually bundle those together because they're pretty similar from a physical, frequency perspective, right? Some of the more unique things about Bluetooth compared to Wi-Fi, though, is that it utilizes something called frequency hopping, which makes it harder to monitor, right? Which is something I'll talk a little bit more about when we get to why Bluetooth is such a hard technology to research from a security standpoint, right? But I'm sure that at this point, for most of you, Bluetooth is something you talk about in your everyday life, right? Like if you're using AirPods, they're using Bluetooth, right? If you connect your phone to your car stereo system, which by the way we'll be talking about, you're using Bluetooth, right? So in automotive, Bluetooth is mostly used for, well, exactly what I mentioned earlier, right? Connecting to your vehicle's stereo system, sharing your phone book with your car, right? That's a source of confidential information, which is of course of interest from a security perspective. But the main task delegated to Bluetooth is not, a very high impact one. It's mostly just controlling your music, hands-free phone calls, etc. And things like your phone book access, so that you can actually see who's calling you when you're on the road and you receive a text message. Some cars will actually support text message integration too, right? This is the basic use case for Bluetooth in automotive, right? And this is probably common sense to a lot of you, but what might be less common sense is how the Bluetooth protocol is actually organized. So I said Bluetooth protocol, but Bluetooth itself is actually a specification. It's not one specific technology. It is a set of specifications maintained by a company, or rather it's a group of companies called the Bluetooth Special Interest Group, right? They manage the specification for Bluetooth, they publish the standard, and they kind of monitor how it's performing, make updates to it whenever a new version of the technology comes out. But at the end of the day, it's up to each individual manufacturer to actually implement the Bluetooth, stack on their hardware however they like, right? And so this is where we get to the big divide in the different protocols that make up Bluetooth, right? So you can see on the screen here, I have the different protocols that make up Bluetooth split into a couple of categories. We have the blue ones up here, the RF-COM, right? Radio frequency communication, SDP, service discovery protocol, L2CAP, this is logical something. I don't remember what this stands for exactly, but it's one of the higher layer protocols, right? And then down here you have the ones in red, right? This is device manager, link manager, baseband resource manager, link controller, and the PHY, right? And then in the middle you have the host controller interface, right? Which begs the question, what does that mean, host controller interface? Well, I made this box here purple for a reason, right? So the ones on the top, they're blue, right? These are controlled by the host, right? Your operating system. Your operating system will have its own Bluetooth stack, and according to that Bluetooth stack, it operates in a certain way, right? So for those of you who are familiar with Linux, BlueZ is one of the more common Bluetooth stacks running on most Linux distributions, and it's made specifically for Linux, right? But then the controller side, right, we have host controller interface, right? So the reason this whole architecture exists is because it makes it easier to interface with different hardware from the actual hardware manufacturers, right? Because they kind of abstract away everything that happens down here through the host controller interface, the host doesn't need to worry too much about what's going on down here, right? So these are controller side protocols, right? And these are each one of these is going to be programmed a different way based on the actual manufacturer of the hardware itself. And by the hardware, I'm not talking about your laptop manufacturer, I'm talking about the actual Bluetooth chip manufacturer, right? So going over a short history of Bluetooth security, right? When Bluetooth first came out in the early 2000s, there were a lot of gimmicks that exploited like protocol level issues in early Bluetooth, right? I would call these I call them gimmicks because they're kind of like, okay, the first time they designed it, they decided encryption wasn't important, so they didn't include encryption, right, for certain things like that, right? So a lot of these were fixed in 2007 when the Bluetooth 2.1 plus extended data rate update arrived, right? This introduced mandatory encryption for connection-based data, except for service discovery protocol, and it introduced secure simple pairing, right? So legacy pairing was the process by which Bluetooth devices connected before this. They would the only way you could pair two devices was through inputting a pin, right? So a 4-digit pin, right? So 0000 or 1234, right? This sounds like a good enough way to do authentication for the connection process between two trusted devices, but for some devices, right? Say for example, a pair of cheap Bluetooth headphones you bought online, they don't have a user interface, so you can't really pick the pin that the corresponding connecting cell phone is supposed to put in, right? So they'd usually be hard-coded with something like 0000 or 1234, right? And this was kind of a bad system, and so that's why they introduced secure simple pairing, which introduced a couple of more options for pairing your device. So now they have passkey, they still have the passkey input, but then they also have numerical comparison. They also have out of band, right? Out of band pairing is essentially you pair through a different mechanism other than Bluetooth, right? So you might have like NFC or something else, another technology entirely used to do the pairing, but then the actual data transfer, etc., is done over Bluetooth. And there's another one called Just Works, which is exactly what it sounds like, and it needs to go, to be honest. It's essentially no authentication at all. But that's for things like I mentioned earlier, things like headphones that don't have a user interface, or like a keyboard or monitor where you can actually do a number comparison. They have to have something in place to work, so they introduced Just Works. But anyway, so after that happened, right, after the introduction of secure simple pairing, I got a little bit sidetracked, there was a pretty long period of about 8 years where there wasn't a lot of research done on Bluetooth, right? So most of the old gimmicks didn't work anymore. Bluetooth Low Energy, which came out alongside Bluetooth 4.0, started out pretty insecure and was a pretty hot topic for research, but eventually a lot of those got patched out, and I think nowadays Bluetooth Low Energy is getting closer to traditional Bluetooth's security grade, right? And so what I mean by the traditional Bluetooth security grade is after all those protocol level bugs got hammered out, it wasn't as easy to research Bluetooth, because if you think about it in comparison to Wi-Fi, right? I made that comparison earlier because they're very similar from the physical perspective, that they both occupy the 2.4 gigahertz space. Bluetooth uses that frequency hopping, which makes it a little bit harder to analyze. You can't buy a $10, $15 Bluetooth sniffer online and just monitor Bluetooth traffic going through the air, right? Another thing, so I have a couple of these listed, right? These problems surrounding Bluetooth security research, right? So one of the other problems, I mentioned earlier that it's not a specific technology, it's a specification defined by the Bluetooth Special Interest Group, and that the implementations will vary based on the operating environments and the chip firmware implementations, right? And I also talked about how the frequency hopping means so you can't actually sniff it out of the air like you can with Wi-Fi. There does exist equipment for that, but that's going to cost about $20,000 minimum, right? Like these are very high grade, like I would say like government military grade equipment. You cannot be expected to buy this if you want to do research on Bluetooth, right? So, and then what I mentioned before, right, I'm going to go back a couple slides and show you the breakdown of the different protocols, right? It's not as easy to analyze the lower level protocols as it should be, right? Because if we think about this here, right, so you have your host layer protocols, right, RF-COM, SDP, and L2CAP, and these are decently, well explored, and the host controller interface exists, and you have the ability to log host controller interface data on all Linux and all Android platforms, which I'll be showing later on in the presentation. But all of these red processes, all of these red protocols are essentially a black box. And because they're going to be so different from manufacturer to manufacturer, there's no real understanding of what's going on inside these chips, right? So that's another reason why security in Bluetooth has been kind of on the down low for a while, up until pretty recently, right? And I said the spec is very complicated, and that is a big part of it, right? Because there are certain parts of the Bluetooth specification that you wouldn't from a security perspective, you wouldn't assume that somebody read this and said, yes, this is okay, and then put it into the spec, and then it went undetected for since the birth of Bluetooth until last year, actually, right? This scenario I'm talking about actually happened. A vulnerability was released that essentially disclosed the fact that any Bluetooth device, when it's pairing with another device, it has the option to negotiate the entropy of the encryption keys used for the communication, right? Okay, sounds like a good idea from one perspective, right? You have the option to, if you have hardware that only supports, say, a couple of bytes of entropy, you can negotiate, say, okay, well, I can only support this much, so can you please lower the security of the communication, right? It's a compatibility thing. But the researchers that published this vulnerability found out that the minimum, according to the Bluetooth specification, right, the minimum allowed entropy for this encryption was only 1 byte. So they could forcibly, by modifying the firmware of one of their devices, they could negotiate down the connection, the encryption entropy of the connection they were making down to 1 byte of encryption, right? And 1 byte of entropy for encryption, is enough to essentially brute force in real time and monitor Bluetooth communications, right? If you have some cheaper hardware, you don't need the $20,000 hardware, you need some slightly less expensive hardware, and you can actually sniff some of the packets out of the air, right? That vulnerability itself is pretty interesting. It's called KNOB, right? KNOB, right? It's an acronym for Key Negotiation of Bluetooth. I'm not going to go too far in detail on that one because I have a couple more things I want to talk about. But that is a good segue into the fact that recently there has been more of a look at Bluetooth security, especially from some labs out in Europe. Right, they have been putting out a lot of great research that I'll have linked to in the end of this demonstration, right? But back to the automotive things, right? I'm kind of going in circles because there's a lot to talk about here, but coming full circle to the automotive side of things, this is a diagram from a piece of research that was published by Tencent's Keen Security Labs, right? They published this in March of 2020, so this is really cutting edge research, right? Basically, there were some unpatched Bluetooth vulnerabilities on some Toyota vehicles that were in circulation that had been made outside of Japan, I want to say as early as 2016 or 2017, right? Unpatched Blueborn led to daemon level access. For any of you that have followed Bluetooth security at all, you might have heard of Blueborn before. Blueborn was a series of high-profile Bluetooth vulnerabilities that were released, or I guess publicized, I believe in 2017 by Armis Labs, right? That's the name of the lab that came up with these vulnerabilities. It was essentially the ability to remotely execute code on any device that had Bluetooth enabled, even if the device wasn't in discoverable mode, right? Discoverable mode is when you make your Bluetooth device visible for the intent of pairing with another device. You have to make it visible through discoverable mode just so that it's easier to find, right? But they essentially showed that even through, without having to pair with the device, without the device being in discoverable mode, they could execute code on any device running Bluetooth remotely, right? So the scenario behind this disclosure, right, that happened this year by Keen Labs, they showed that through exploiting these unpatched vulnerabilities in these automotive head units, right, inside these Toyota/Lexus vehicles, they were able to gain daemon level remote code execution because the Bluetooth service on the main board here, right, this board here this is a wiring, a logical diagram of the inside of that head unit, right? This main board, which is running the Bluetooth service, was running Bluetooth at a pretty high privilege. Right, it was running it at a daemon level privilege. So from there, they were actually able to get remote code execution, escalating privileges to root, and establishing a Wi-Fi backdoor was the next thing they did, right? So they made a Wi-Fi backdoor that allowed them to SSH back into it from a slightly longer range than Bluetooth allows, right? Because Wi-Fi has a better operating range than Bluetooth does. And through that, they were then able to make use of this main board's position inside the head unit to actually push updates to some of the other devices inside the head unit, right? Specifically this UCOM board. This UCOM board is connected to the CAN buses that the head unit itself is connected to, right? And for those of you who are coming from an automotive background and just wanted to learn a little bit about Bluetooth, you know that being connected to the CAN bus is essentially getting access to the car's nervous system, right? This is the in-vehicle, the controller area network, the in-vehicle network, along which a lot of the vehicle controls happen, right? So, long story short, I could talk about this particular bit of research for about an hour on its own. But long story short, Bluetooth vulnerability led to further exploitation, and the installation of a backdoor, which allowed the researchers to reflash this UCOM board, which, by the way, didn't have any checks on the software that was pushed to it for updating it, right? Which is an entirely separate problem. But we're then able to pivot from there onto both the CAN buses, the dedicated CAN bus and the infotainment CAN bus. One of the lucky, I suppose, features of this entire scenario is that the CAN buses were pretty well segregated by this central gateway ECU. So despite having this foothold, right, it was a big deal that the vehicle's steering, braking, and acceleration were actually not affected, right? I believe that is in part due to the central gateway in place and the fact that the different CAN buses were physically separated. But anyway, that's a good, just a good point to keep in mind. I'm going to double check and make sure there are no points I missed. So yeah, one of the things that they had to do the updating for was the ability to remove filters on arbitrary CAN message sending, right? So that's the update that they actually sent to the UCOM board, was the ability they added the ability to send arbitrary CAN messages. The full technical report isn't out, but it's hopefully scheduled to be released in 2021. And it really, anybody can say how well the rest of 2020 is going to go. But anyway, we have now time for a live demo, right? So this is going to be a quick demo showing how to get started with Bluetooth in a Linux environment. As always, when it comes to live demos, something always goes wrong. I actually have a automotive head unit that I was hoping to show a live interaction with it through Bluetooth, but unfortunately today it decided it didn't want to stay on. So I'm going to be actually just showing how those Bluetooth tools work, but I'm going to be using my cell phone as the target for analysis instead. So I will switch over to my virtual machine and we'll head right back into the recording. Okay, so let me increase the font size here. How's that look? A little bit bigger. Okay, so for any of you wondering, I'm running a stock Kali Linux distribution on this virtual machine, right, running on my Windows desktop. I don't have anything incredibly interesting installed from a Bluetooth perspective, right? So all of the tools I'm going to be showing are actually available in Kali Linux, as fresh upon installation, right? So there's no fancy software, there's no secret hardware I'm using. I'm just using the Bluetooth chip inside my computer. I want to give a disclaimer that sometimes things get a little bit strange if you use Bluetooth through a virtual machine. The reason is because your virtual machine and the actual hardware and your actual host machine are sharing the same hardware, right? The same Bluetooth hardware. So if I start connecting to something with my virtual machine, it will sometimes confuse the host machine, and that's, it's a little bit of an annoyance, but for the sake of today's educational demonstration, I think we can live with that, right? So the first thing I need to say, of course, a disclaimer that I'm not going to be showing any vulnerabilities or exploits that could lead to compromise of any systems, right? I'm just going to be showing some basic surveillance tools and showing what you can find very easily with the proper knowledge with some open source software. I'm not talking about anything incredibly expensive, you know how it is. But it's important that we understand, the whole purpose behind all of this is that we understand what security risks might be present in the vehicles we operate, the other devices running Bluetooth, any privacy concerns that might be, unaddressed otherwise, right? We don't learn these things in order to harm people. We use these techniques to arm ourselves with the appropriate knowledge to protect ourselves from those who may do us harm or may mean us harm, right? Anyway, so now that that's out of the way, let's get to the actual interesting stuff. So the first thing I have to do is sudo service Bluetooth start. right? Put in my password and let that work, right? So a lot of times, I don't know why this is, but the Bluetooth service will actually be disabled by default, right? When you start up your device, you can actually change that in your settings so that it turns on by default, but whether or not you want to do that is up to you. But in any case, the next thing we're going to do is check what Bluetooth controllers are available on our machine. So that's done in Linux with HCI config, right? That's host control interface configuration. So this now here shows all of the devices I have, all the Bluetooth devices. I have just one right now. I have my internal, my laptop's Bluetooth chip, right? Primary bus is USB. Depending on how your computer is built, this might actually be something different, like I2C, right? So on and so forth. But the way mine is set up to be USB. You can see the Bluetooth address of that Bluetooth chip, right? Mine is currently up and it's running a pscan right now, right? You can see a lot more information if you say sudo hci config -a, right? We can see a little bit more now, right? So we see the same information as before. We have the Bluetooth address, we have the status, it's up and it's running. We see I haven't really sent very much, so I don't have any errors, nothing incredibly special is happening here. Most of this information isn't incredibly useful, right? Like off the bat, it's not incredibly useful. I'll be perfectly honest, right? But there are a couple of interesting things here. For example, the name, right? Name is Kali. This is how my device appears when I go into discoverable mode and another device kind of scans me or finds my device through its scan for Bluetooth devices. Because that's how Bluetooth devices find one another, is they do a scan, and any device that's discoverable in your area, you'll be able to pick up on it, right? I'll be showing that in just a quick second. So more than that, there is this class object here, right? So the class in this scenario is talking about the class of device. This, this 1, 2, 3, 4, 5, this 3-byte number, or hexadecimal number, is actually used to identify what type of device belongs to this, or this Bluetooth chip belongs to. So the class will identify your device as a phone, as a laptop, as a desktop, as a pair of headphones, so on and so forth. Sometimes this is a big deal, right? Because if you think about a car, most cars aren't designed with the expectation that they will connect to a laptop over Bluetooth, right? It's not like the most outlandish thing to think in the world, but a lot of cars will actually refuse Bluetooth connections from devices that have their class identifying them as, a laptop or a desktop computer. So depending on the actual type of Bluetooth chip you're using, you might be able to change the class of device that your device actually identifies as, right? So I don't believe I have the ability to do that with my internal laptop Bluetooth chip, right? This is entirely a metric of the Bluetooth chip installed inside my laptop. I'm actually going to go ahead and give it a shot and see if I can change it, right? But the first thing I'll do is I'll show you guys, right? HCI config HCI0 class. This will give us a little bit more information about what my class is reporting, right? Currently my class is set to 0C0000. This is actually, I think, because I'm using a virtual machine, right? It's just labeled as miscellaneous. It doesn't have a actual, real class of device because this is a virtual machine, right? But let's see if I can't change it, right? I'm actually doing this for the first time. I've never done this myself on this machine. But if I go for sudo HCI config HCI0 class, and I enter the class ID, I want to set it as 0x5a020c. I know that's for cell phone. Let's see if that worked. Oh, there we go, right? So now I've successfully changed the class of device associated with my Bluetooth chip to that of a cell phone. So see, the device class here now shows phone, smartphone. So you might be familiar with this, like when you're trying to pair your phone to your car, right? When you're searching for your car on your cell phone in the Bluetooth menu, it'll actually show like a little symbol next to each device, kind of giving you an idea of what kind of device that is, right? Is it a pair of headphones? Is it like, it'll show like a laptop, like a little, clip art laptop if it's an actual computer, right? Or if it's another smartphone, it'll show a smartphone. So now when I scan or go discoverable with my laptop, it will display itself as though it was a smartphone, right? And this is useful for spoofing if you want to copy someone else's device and try and do some research on intercepting a pairing request, for example. That's you're getting very, very creative there at that point, right? But I'm glad this worked out. This gives me something to show for. But anyway, on with the demonstration, right? So the first, in general, when you're doing a security test, the first thing you need to learn how to do is actually find what you're looking for, right? And so that means you need to scan. So HCI tool scan. Because like I mentioned before, the actual device I'm using, I wanted to use, the extracted head unit, currently isn't working. I'm going to actually turn Bluetooth on my smartphone, and we're going to see if I can't find it by scanning. All right, so HCI tool scanning. I'm currently discoverable, so it should pop up any minute now. If it doesn't, I'll have to think fast because, well, okay. Anyway, here we go. Okay, so these are my headphones, right? The name is in Japanese, so don't worry about it if you can't read it. But this here is my cell phone, right? It shows my cell phone's name, right? This is the name that my cell phone broadcasts itself as over Bluetooth, and this is my cell phone's Bluetooth address, right? I don't mind sharing this information. There's not a whole lot you can do with this, but there is a little bit more than you think that you can do with this, right? And I'll show off some of the features of what's actually contained inside a Bluetooth address in just a second, right? So this basic scan here gives us a very basic idea of what's around us, but if we say instead sudo HCI tool info, and then I copy this, right, and paste it into my command line, it's requesting information from my phone, and now we have this whole little dump here. This dump is great, right? This is really like the first thing you want to do when you're testing a Bluetooth device. And I'll show you why. The first thing it shows you is the OUI company, it's the organizationally unique identifier company, Samsung Electronics, right? I've been exposed. I'm using a Samsung phone, right? So you can find out what kind of phone I'm using without ever looking at my phone just by scanning my Bluetooth address, right? The reason for this is because the first half of a Bluetooth ID is actually this OUI. It's the organizationally unique identifier. This identifier identifies Samsung Electronics Corporation, right? You see that DC7488? It's right there, right? So all Samsung Galaxy S8 Pluses, I assume, will have this same Bluetooth address. I don't know if there are like sub classifications for this, but for example, what I mean by that is if there are, how should I say? I don't know if there are like lots of different Samsung Electronics OUIs. Maybe there are. I don't know exactly, but it might be. But the point is, there's actually a website, where you can go and look up. I believe on the Bluetooth Special Interest Group's website, they have a OUI lookup tool, so you can find any OUI, right? If you find it, just by war driving in the street or something, and you find a device, but it doesn't return here, you might be able to look it up on the website and find out what kind of device or what the manufacturer of that device was, right? More interestingly here, right, is the actual LMP version of that device. So the LMP is the Link Manager Protocol, right? This is showing the version of the Link Manager Protocol that I'm running, right? And this information might come in handy because, obviously the more information you have on your target, the better. You have more vectors by which to search for vulnerabilities or other ways to compromise the device, so on and so forth. So this is always a good bit of information to have, because this will also give you information on what actual version of Bluetooth that device is running, right? But going on, so here, the manufacturer tab here, this is usually a big deal. I want to see if I can't find another Bluetooth device. Like, let's actually scan this one instead, because I think that Samsung decided to obfuscate this, so it's not actually showing what the manufacturer is, but that manufacturer field is actually supposed to show the chip manufacturer. Okay, so this one isn't showing up either. This could be because I'm doing this on a virtual machine, I don't know why this is not showing an actual, how should I say, an actual company's name. Normally this will show something like Broadcom or Cambridge, you know, like any of the actual chip manufacturers, their name will usually show up here. This is the first time I've seen the whole not assigned thing, but well, not everything can go right? I mean, we already lost the head unit I wanted to test on, but anyway. So, but you know, now that we're here, we scan my headphones. You can see they're Bose Corporation, right? So any company that's making Bluetooth devices will usually have their own OUI registered, and you can find that out through here, right? I'm still not sure why this isn't showing up, but it's normally it does. I promise, right? I'm not making that up. Let me try and add one more device onto my Bluetooth network and see if I can't scan it and introduce another test subject. So let's scanning. I just turned on my Xbox controller, so let's see if I can't find this through the Bluetooth scanning here. Aha, okay. So we have this new address. Let's copy that, and let's come over here and paste it. Let's see if we get lucky this time. So once again, not assigned. I don't know what's going on here. I suspect it might be an issue with the virtual machine setup, but that's surprising in and of itself. Anyway, so I've kind of gone in a circle here, wasted some of your time. I apologize for that. But let's get on with the rest of the tools, right? So after scanning, I mentioned earlier that one of the protocols running on the host side of Bluetooth is the Service Discovery Protocol, right? So Service Discovery Protocol is the only connection-based protocol that doesn't require encryption. And this is because what Service Discovery does is it advertises what services, you know, what functionalities this Bluetooth device has, right? If it's a car, it's got to have, you know, phone book access, it's going to have audio visual control. Each of these is its own set of functionalities that's, you know, dictated by those services, right? We call those services. So the way you actually look at what services are available on a device, right? Let's go back to my cell phone and copy this here, right? We'll copy that. So if we come back down here to the command line and we go SDP tool, right? Service Discovery Protocol tool, browse, and I just paste that. And let's see if we can't ask it for some information. So sometimes it will refuse it based on the device. Sometimes you have to be paired with the device before it will actually concede any information to you, right? This is, and the embarrassing part about this is that I wish I could tell you that all of these tricks worked 100% of the time, the first time, every time. And sometimes that doesn't actually work. Right? Sometimes you have to just try it more than once. Sometimes the device just doesn't want to talk to you unless you do a fully established connection, right? So it looks like my cell phone is being pretty stubborn today, but okay, I might have to come back to this after I try and connect to it. Okay, yeah, so it looks like it's not working. But anyway, we're going to skip over Service Discovery Protocol, and we're going to look at another part of Bluetooth in Linux, right? This is the last main thing I'm going to be showing. This is Bluetooth CTL. So Bluetooth CTL is short for Bluetooth Control. This is the agent that BlueZ, right, the Linux Bluetooth protocol stack, uses to manage connections and stuff. So when I enter this, you know, Bluetooth Control, I get this like special little different terminal here, right? It's like blue, and I have my own separate set of commands, right? Each of these is its own talk in itself, so I can't really go too far into detail, but I'll show you all the important ones. So the first one you want to show, or I'd like to show, is list, right? List will show me all of my controllers, and it will tell you which one is the default controller, right? So this is important because sometimes you'll have more than one controller on your system. For example, if your controller, the internal controller, Bluetooth controller on your system doesn't allow you to change the class, for example, a USB, you know, an external one might allow you to do that, right? So you might have two, and then you need to select which one you want to use. So in my case, I'm going to say select to a tab complete. Yeah, it's my only one, so it's kind of redundant to do that, but it's a good thing to know how to do, right? So devices. what did my devices show? So I have these are not my AirPods. These are one of my friend's AirPods, but they're there. And if I go remove 504, will that remove them? Yes, it will, right? So now I go back to devices. So now we're back to an empty list of devices, right? So devices is used to show all of the, well, devices that you've encountered, right? So let's see if there's a part of this help screen here. It doesn't actually show. No, it does. Yeah, it lists the available devices. So anything that you've scanned, anything that you know is in your vicinity, right, will appear in that devices list. I removed this because these aren't with me right now, so they're not actually around here. But let's go ahead and turn on the scanning feature of Bluetooth control. It's a little bit different from the HCI control, but set scan on and then see what shows up, right? So as before, we have my phone, right? It shows up as a new device, which is now populated in my devices tab. And from here, I can go ahead and connect to it. Oh, there are my headphones again. Let's turn the scan off now because I've got my target device, right? It's already shown up here. There's no need to keep poking around and exposing my neighbor's Bluetooth devices. But from here, we have a couple of more cool things we can try. We can say info DC, right, and see what we got. You know, through this interface here, we have a similar dump of information that we got when we used HCI tool info, but here we can actually see the class of my cell phone, right? So it's showing that this is class 005A020C, right? This is the same one that I changed my internal computer to, but it shows like, you know, it shows what the class of the opposing device is, which might be useful information, and you know, icon is going to be a phone, not paired, not trusted, so on and so forth. And it does support legacy pairing, right? This might be a piece of information that you're interested in, right? Depending on what you're looking for. So let's go ahead and actually try and pair with my phone. Let me just unlock this thing and get to the pairing process. So if I say pair DC, attempting to pair with this. Okay, it says connected. Yes, so I have a connection. Okay, I have a added device. I'm gonna hit OK on my phone. Because I'm doing this in a virtual machine, this might not work as I hope it will, but it's something, right? Okay, so now I have, it shows Alendite here saying I'm connected to it. I'm gonna actually open a new tab and say SDP tool, browse this, and see if this time we get a response from it. Hopefully this will work. If it doesn't, I'll have to include like a post recording, like screenshot of what the output of this tool looks like, but I'd like to be able to show it live if possible. Yeah, I knew doing this on a virtual machine was a mistake. Okay, let's try this in sudo. I don't know if it got stalled somewhere before reaching the actual communication part, because it's not showing the requesting information part that it was last time. Yeah, in my experience doing Bluetooth, a lot of times things just don't work that's the second time, right? Like they just don't. Okay. So as embarrassing as that is to admit, this is a genuine part of working with these tools, right? So here, if I come here and I say paired devices, okay, so this didn't work. Well, let's try pairing to it again. Like, okay, oh, failed to pair in progress. Okay, hold on a second. Failed to connect. Operation now in progress. Okay, everything is going wrong right now. Okay, remove DC. Okay. Oh well, authentication canceled. Okay, we have removed it. No longer my devices. Yep. Okay, so let's try this again from the top, right? And no matter what the demo shows you, this is what working with Bluetooth is actually like. Right? Sometimes it's just a real pain to deal with, so we found it again. Here it is. I'm going to copy that. I'm going to say pair this device. Attempting to pair. Yes. Okay. And says I'm connected, but my phone is no longer receiving the request to pair. Right? You saw earlier how when I asked it to pair, the window, this was a Windows notification that showed up saying like, click here to set up your Bluetooth device. That's because I'm running a virtual machine. The host OS actually kind of grabs that connection and is like, what would you like me to do with this, right? So I think that I'm gonna have to call it here for the Bluetooth demonstrations just because of the limitations of my hardware right now, because I don't have an actual Linux machine that I can run this on bare metal, unfortunately. But anyway, hopefully, despite all of the hiccups I ran into along the way, you were able to learn something about Bluetooth hands-on. I'm going to switch back over to the PowerPoint and just give you guys some resources to try out and some other, just some closing remarks before ending this talk. So let's go over there real quick. All right, we're back in the PowerPoint, and the last thing I want to go over is a couple of tools that I would suggest looking into for anyone who's new to Bluetooth and wants to, get into Bluetooth research, right? This is a great time to be getting into it. I'll point out why I feel that way in just a second. But here listed on the screen are a couple of resources that I found very helpful in the past, and I think that are very relevant for modern day Bluetooth, understanding, right? So pull out the laser pointer. So first and foremost, BlueZ, the Linux Bluetooth stack. There are APIs available for both Python and C. There is a guide online that I have linked in the next slide. It's kind of old. Okay, it's not kind of old. It's really old, but it still does a decently good job of explaining how to get started writing your own very basic Bluetooth programs, and just running through that it's a pretty short textbook, but running through it is a good way to just get more familiar with how Bluetooth works, what the different components are, what kind of access to Bluetooth you have through BlueZ on your Linux system. I definitely recommend reading that book. Like I said, it's linked in the next slide. Bluetooth Stack Smasher, this is a fun little tool that was made a long time ago. It's not likely going to get you an awesome pwn of a head unit, right? But it's essentially an L2 cap layer packet fuzzer, right? It will just blast random data at the L2 cap layer at a given Bluetooth address of your choice. It's very, very simplistic, but it has some has the ability to, you can actually customize the frame, or the data that it sends out to the target device. So I've used it before with varying degrees of success, but it is good to know that it exists. It's about as good a over-the-air Bluetooth fuzzer as you can get. SpoofTooth, this is another quite old one. This was a project made for the express purpose of spoofing nearby Bluetooth devices. So it makes it a lot easier to do what I was showing, like with the changing your class to copy a device, and you can change your Bluetooth address too, if your Bluetooth chip allows that, of course. So SpoofTooth kind of simplifies that process, of course, based on the allowances of your hardware. And then Internal Blue, this is really a big deal. I think that the lab doing this research here, this is the CMO lab, somewhere, I don't remember the country they're based out of, but it's somewhere in Europe, and they are the ones who have really kickstarted a lot of the recent Bluetooth research. So I mentioned before the knob attack, right? The key negotiation issue that was part of the Bluetooth protocol. That was discovered because the researchers who found that were using this Internal Blue. This is a framework for re-flashing Broadcom Bluetooth chips and essentially using them as very flexible Bluetooth adapters, right? I won't go into too much detail because I'll be honest, I'm not really qualified to talk about it. I don't want to say anything incorrect and have you all assume that I'm qualified at that level. But it's really, really great. They have a lot of talks published. I believe they published a couple more recently that I still have to watch. But just going to their GitHub page will give you access to all of their papers and, recorded presentations, so on and so forth. And I think everyone interested in Bluetooth could definitely benefit from checking them out, right? So speaking of the references page, this is my references page. The Introduction to Bluetooth Programming is the BlueZ one that I talked about before. The Internal Blue GitHub, definitely a great resource for anyone, like I mentioned. The knob attack, this is if you wanted to read more about the knob attack or Blueborn, right? These are the two vulnerabilities that I talked about to some degree of depth in this presentation. And lastly but not least, this is the link to Bluetooth Stack Smasher. the tool that I mentioned before for L2 cap fuzzing. So hopefully you find any of these useful. Hopefully you learn something. Hopefully this will help you out maybe in the CTF for our virtual car hacking village. If you have any questions, of course, I'm always open to be emailed, right? Just send me an email at kamel.gali@whitemotion.com. I'm happy to provide you with these slides or any other resources if they're something that I own and I'm, free to share. But hopefully you have a great DEF CON, and yeah, on to the next Car Hacking 101.
All right, Camille, thank you very much for your talk. I love this talk about Bluetooth security. Thank you very much for your talk. If you guys have any questions about Bluetooth and security, even just car hacking in general, this is what the CHV101 is all about. It's all about learning where the building blocks are. Where do I take the first steps? So, and if you have questions, we have the experts here in Car Hacking Village to help you figure out what that means to you. Where's the interest? Where are the resources, the mentors, and everything? So, guys, if you have questions, please write them in the Car Hacking Village 101 support channel. We'll be happy to help you. The next talk that's coming up is Automotive Ethernet for the rest of us. It's going to be a short talk about what does Automotive Ethernet do for us? What could we do? And Infinite is going to give that talk again. So looking forward to that. It's going to happen in around 9 minutes. Okay, so check back in soon. All right, guys. Thank you. All right, welcome back to Car Hacking Village 101. The next talk that we have is Automotive Ethernet for the rest of us. Infinet is going to give this talk. It's going to be an interesting talk about Ethernet and what do we do with it, why is it in vehicles, and so on. If you do have any questions, please go over to the Discord channel, CHV101 support text, and ask your questions there. We have the experts on the line helping out. Also, if you are joining us from Twitch, or YouTube, or wherever else it might be streaming, please, head on over to the Discord channel, discord.gg/defcon. There's so many villages going on, not only the car hacking village, but there's just so many different conversations. So check it out. All right. Without further ado, I would like to introduce Infinet and his talk about Automotive Ethernet for the rest of us. Infinet, it's all yours.
Automotive Ethernet for the rest of us. What is Automotive Ethernet? Who uses Automotive Ethernet? Why use Automotive Ethernet? And some technologies to know. Who am I? Xavier D. Johnson, otherwise known as Infinite on Twitter, born and raised in the Motown, hacking around since about 12, first mentor for Team 94, TechnoJays, organizer of DC313, director for MySec Detroit, and I host a show on YouTube called How They Got Hacked. Enough about me. Let's dig into what exactly is Automotive Ethernet. So, electronics in a car, they're split up into these things called domains. Powertrain domain, body and comfort domain, the human machine interface, driver assistance, chassis. These things do anything from control steering and braking all the way to controlling your radios and your windows and your seating, as well as allowing humans to be able to interface with controls that via interfaces, things that actually control the machine. Automotive Ethernet is a physical network that is used to connect components within a car using wires. So why was Ethernet not used in vehicles before now? Well, Ethernet didn't meet the OEM requirements for the automotive market. Basically, 100 megabits per second and above Ethernet has too much radio frequency noise, too much alien noise on the wire from other devices inside of the car. So Ethernet cannot guarantee low latency due to the low microsecond range that is required by vehicles. And this was a hard requirement to replace any communication that needs fast reaction times. Also, there was no way for Ethernet to be able to do time syncing between devices and having multiple devices sample data at the same rate. So what are some of the use cases for Automotive Ethernet then? Well, the different drivers of Automotive Ethernet come from, of course, those domains that we spoke about earlier, the complexity of the components and the wiring harness to a vehicle. The wiring harness is actually the third costliest and third heaviest component in a vehicle, right? So talking about cost, there's been a joint study between Broadcom and Bosch that estimated using UTP cable to deliver data at a rate of 100 megabits per second, along with the smaller and more compact connectors, can reduce connectivity cost up to 80% and cabling weight down by 30%. So, when we talk about the data rates via unshielded twisted pair, the electronics in cars are becoming much more complicated, more controllers, more sensors, more interfaces, and all of this stuff requires higher bandwidth. So these are some of the drivers behind the main motivators behind using Automotive Ethernet. So technologies that are entering the automotive space include self-driving, connected cars, augmented reality, vehicle-to-vehicle communications, and things like self-driving require lasers and radars that can process anything, things much more faster than humans can, and more reliably than humans. And we can use these tools and these advancements to be able to do things more efficiently and more effectively on the road, doing things like platooning, where cars get close to one another so that they can occupy less space on the road, and parking very closely in parking spaces. Augmented reality, things like dashboards for the driver to be able to look through the windshield and see things at a distance and be able to understand exactly, what those things are and categorize them and how far exactly they are away, and how fast the driver's moving towards it. If there's danger, arrows could appear and let you know exactly how to avoid the danger. And then these technologies are considered for passengers as well, right? Connected cars, which we're living through right now with the advancements in cellular and Wi-Fi connectivity. This allows us to be able to communicate and do video streaming, as well as remote diagnostics and updating firmware, which usually require access to the internal networks and computers in cars. So vehicle to vehicle communications allow cars to be able to speak to one another. The NHTSA estimates that by using V2V, 79% of target vehicle crashes would be avoided. So that we're talking about huge benefits and safety just by allowing us to be able to increase the amount of technology sensoring in the vehicles, but we're going to have networks that can actually handle that bandwidth and capability. Digging deeper into these technologies, right? So AUTOSAR, the Automotive Open System Architecture, one pair Ethernet, otherwise known as open, power over Ethernet or PoE, energy efficient Ethernet EEE, time synchronization, as we talked about that being a problem before, AV bridging, diagnostics over IP, which is extremely exciting, and time triggered Ethernet. So digging into AUTOSAR, it's an open, standardized automotive architecture jointly developed by manufacturers and tool developers. TCP, UDP, IP stack that is used in automotive components, and is basically the standard that all of the automotive industry came together and decided to agree on versus just fragmenting out and working in silos. Broadcom made a physical chip, PHY, a standard called Broad R Reach. This is allowing us to be able to enable longer distance copper Ethernet connectivity at a sustained 100 megabits per second. It's using technology from 1GE copper, including multi-level PAM3 signaling, better encoding, echo cancelers. These allow for bi-directional data flows on a single pair. Due to lower bandwidth, this standard met the automotive EMI requirements, and Broadcom started marketing this to the automotive world. Power over Ethernet. It's used to further reduce the wiring needed, since you can actually power the end devices as well as sending data over that wire at the same time. So you're able to power the device as well as get data over it without the need for having extra wiring to power the device. Energy efficient Ethernet. So when you're dealing with cars, not all of the electrical components turn off when the engine is turned off. So with that being said, you have a drain on the battery, and to minimize that, energy efficient Ethernet turns off the network when it's not in use. So the components that don't need to be powered on stay off until the engine turns on. This is to help with minimizing power consumption. And then, so time synchronization, we talked about this. Time is a must. It needs to be synchronized between all the nodes in the car. So the IEEE 802AS, 802.1AS, timing and synchronization for time sensitive applications and bridge local area networks is the standard to actually synchronize timing. This uses a profile and introduces simpler, faster methods for choosing a master clock. Time-triggered Ethernet. Many controls in the car require communication latency in a single microsecond range. Literally, so controllers can get sensor readings to control functions of vehicles. If we're talking about self-driving cars, we want to make sure that the sensors have communication latency that is extremely low. So time-trigger Ethernet simplifies the design of this, creates fault tolerance and high availability. The safety and redundancy are maintained upstream at the network level without any need for the application to be involved. So for AV bridging, 802.1 QAT, also known as stream reservation, is a simple protocol to notify the various network elements in a path to reserve the resources needed to supply a particular stream. And 801.1 QAV, the queuing and forwarding for AV bridges, defines rules to ensure that an AV stream will pass through the networks within the delayed specified time in the reservation. ISO 13400 is a standard that is adopted by the automotive industry to both read out diagnostics from the computers in the car and update firmware in the car. So this covers our diagnostics over IP portion. The protocols run over TCP/IP and are used both on dedicated diagnostics Ethernet connections as well as over the air systems such as GM OnStar. Thank you very much. I hope that you learned a few new things about automotive Ethernet. And if you have any questions, please don't hesitate to hit me up on Twitter.
All right, Infinite, thank you so much for your talk about automotive Ethernet. Really interesting use cases and how it's going to be used in the future. Really nice. So the next talk is actually coming up in around 50 minutes. So, and this is a really great talk. Jamie Lightfoot is going to be describing how cars talk to cloud and talking about this MQTT messaging structure. So if you want to learn about how the cars are communicating with cloud or the cloud with the car, come back, join us here in about 47 minutes, and we'll have Jamie Lightfoot with us to talk about MQTT. All right, we'll see you here soon. All right, welcome back, DEF CON, to Car Hacking Village 101, where we try to explain the basics, bring the knowledge into the people that would like to learn about how to hack cars. So our next talk is car to cloud talk using MQTT for car hacking. Jamie Lightfoot is going to be presenting for today, and looking forward to her talk. If you have questions, please go ahead and submit them into the Discord CHV101 support text channel. I will be there with a bunch of other experts as well to answer your questions and to help you get into this whole area of car hacking. If you are joining us from Twitch or YouTube, please go ahead. You can come join in the discussion on Discord, discord.gg, DEFCON, and ask your questions, give comments, discuss things, let us know. There's also a virtual car hacking village going on right now, so you can actually hack virtual cars. So the guys have developed software and hardware to allow cars to be on the internet. So go check it out. Really amazing stuff. All right, but without further ado, I would like to introduce Jamie Lightfoot in her talk on car to cloud talk using MQTT for car hacking.
Hey everyone, welcome to my talk, Car to Cloud Talk using MQTT for car hacking. My name is Jamie Lightfoot. I used to work as an electrical engineer, and now I work at Grimm doing car hacking. This is a Car Hacking Village 101 talk, which is meant to introduce people to foundational ideas, protocols, and so on used in car hacking. Earlier today, we had talks on CAN, OBD, in-vehicle networks, Bluetooth, Ethernet, and now MQTT. One of these things isn't quite like the others, so before we talk about MQTT and how it works and how you can use it, let's talk about why we're talking about it in the first place. Automotive companies won't directly come out and say it, but if you've got a newer car or truck, then they're probably collecting a lot of information on you and your driving habits all the time. Some of this is sold as safety features like OnStar or other ways of remote assistance where they need to know the location of your car. Some of this is sold as convenience. For example, you've got remote unlock or lock functionality, remote start, remote alarm through a phone app. There's also over-the-air updates so you don't have to go into a dealership. Some of this connectivity is much more for the engineering company's benefit than for the consumer. In a past job, I worked on a project where we aggregated truck engine and transmission data, and we would use that to predict future maintenance needs and ship the repair parts to where we knew the trucks were going to be weeks in advance. We would save the company tons of money on downtime, and we would also get them insight into what kind of warranty claims were going to be coming up. In all of these cases, the data somehow has to get to or from the car to somewhere else useful, like your OEM branded mobile app, some kind of online engineering portal, a dealership tool, or whatever. And that's where MQTT comes in. Most of this talk is going to be about the protocol itself, but to give you an idea of how this ties into an actual car, for newer cars and trucks, we have a telematics control unit, or TCU, which is the PCB in this diagram. The TCU is going to be likely on the CAN bus and accept other inputs from the car, for example, if there's a GPS antenna. So it has the ability to interface with the car, and it also has an understanding of what is currently happening in the car. It'll be able to use its cellular connection to the cloud to send information in the form of MQTT messages. It can also do the same thing in reverse, where it is accepting MQTT messages from the cloud and then taking some kind of action within the car, for example, sending information out over the CAN bus. So in this scenario, the TCU device has to have, at a minimum, the ability to connect to a cellular network, or more likely, networks plural, as coverage is going to vary throughout a given area, and you want to be able to switch between them. And then CAN transceivers, or another way of interfacing with the other parts of what is happening in the car. But if you have a cellular connection from the car to the cloud, why would you choose MQTT over some other method of communication? Like maybe you're able to send a text to the TCU device and wake it up and then have it establish an HTTP connection. The reason is because cars are a bit of a difficult use case from a network and architecture standpoint. You've got unreliable connectivity or maybe varying connectivity quality because you're driving around and you might go through areas with poor signal. So you need to have some kind of protocol that has minimal overhead and size. You might want the ability to buffer messages if you're offline for a minute. And you also might want some kind of method to know if your message was received or not. You're probably dealing with high network latency, which means that you want to reduce overhead as much as possible. MQTT clients will remain connected and they don't need to reinitiate a connection with each message. Whatever architecture you use also needs to be able to scale up to millions of vehicles and handle millions and millions of messages per day. Hopefully you're also considering the security of the system, but we'll talk about that more later. MQTT stands for MQ Telemetry Transport, or Message Queuing Telemetry Transport. It came from Andy Stanford Clark and Arlen Nipper, who were at IBM and Eurotech respectively. IBM had a MQ, or Message Queuing, product at the time. The OASIS standard for MQTT does not use queues to describe the message communication, but that's where the name came from. It was originally made to monitor oil pipelines over a satellite link, so that's where the emphasis on low bandwidth, very lightweight came from. MQTT.org describes it as a publish, subscribe, extremely simple and lightweight messaging protocol designed for constrained devices and low bandwidth, high latency, or unreliable networks. The design principles are to minimize network bandwidth and device resource requirements, while also attempting to ensure reliability and some degree of assurance of delivery. Given the network challenges that we talked about earlier, it seems like MQTT is a good fit. So let's talk about how it works. In MQTT systems, there are two types of network entities. There's an MQTT broker, now called a server, but I call it a broker out of force of habit. You also have one or more MQTT clients. An MQTT broker is a program that receives all the messages from the clients and then routes the messages to the appropriate destination client. It's pretty much like a post office. All messages have to travel through the broker in order to get to the other clients. A client can't send anything directly to another client. A client, then, is a device that is either interested in receiving certain information from the broker via other clients, or publishing information to the broker, which will then be sent on to the interested clients, or both. In an automotive environment, a client is going to be the car, or specifically the TCU unit in the car, and the broker is going to be some kind of cloud service that the car company has set up. A mobile app might also be a client, a dashboard might be a client, but there's usually some more architecture going on, so they aren't all talking unfiltered to the same broker. Here are a few examples of cloud broker services that I have seen or worked with. There are others. These are just a couple options. To visualize brokers and clients, I made this diagram where we have a broker in the middle and a number of clients. Each client can either subscribe, publish, or both. What kind of behavior they do is contingent on how they try and connect to the broker. I will see more about that in a minute. Earlier, I said that it is a publish-subscribe method, or pub/sub for short. Each client can designate what information it wants to publish to the broker, and each client can also specify what information it wants to receive back, and then the broker just doles out the messages as intended. Additionally, clients can provide forms of authentication to the broker, but they aren't directly addressable. So if you have a whole fleet of trucks or cars sending out messages, you probably want to be able to keep the messages separate or organized so you know which messages apply to which vehicle. And that's where topics come in. You can designate topics however you like. However, there are some patterns to follow. Here I've got some example topic names where maybe we have a DEF CON wide broker and there's a topic called Car Hacking Village where if you subscribe to that, you get all the information being sent out related to Car Hacking Village. And then if you publish to it, then everyone who's subscribed will receive that information. But because Car Hacking Village has a lot of different things going on, let's break it down into subtopics where we have Car Hacking Village /talks or Car Hacking Village CTF, where if you're only interested in the talks or the CTF, you can subscribe just to that and narrow down the information that you receive. Likewise, if you're publishing, you are publishing to a more narrowed down audience. And then you can just keep nesting as far as you want. For example, maybe in the CTF we have different team IDs and you can subscribe to your team ID and see what score you have. So if you've got people publishing to each of these individualized nested topics, if you still want to receive all of the information about Car Hacking Village, then you will want to subscribe to Car Hacking Village / either # or hashtag, depending on how old you are, and you'll receive all of the Car Hacking Village topics. If you were to subscribe to the # by itself, that would function as a wild card and give you all topics available on that broker. So for our DEF CON example, it would give you information on all the villages, all the CTFs, all the things happening. But if you are a client, this is probably more information than you want or than that you can handle. If you're a top-level component in the architecture, you're probably interfacing with the broker in a different way to get all the information out. A client can only publish to one topic at a time. You can't publish to a group of topics or a wildcard. For the publishing volume, it's up to the client, but think on the order of maybe once per second. So in automotive, the topics might look like car data and then the VIN number and lock status or location, latitude, location, longitude, information about the engine, and so on, where you would receive back probably JSON. All of that is defined by your system. It's kind of however you want to set that up. You can also use the # and + to selectively handle levels. So you could do car data and then a +, location, latitude, and that would get you all of the latitudes for all vehicles if that level that you're using the + for typically handles VIN data. You could also do car data # or hashtag to get all information, so the lock information, location, engine, and so on for all vehicles on that broker. If you are securing a MQTT broker, you want to make sure that your clients don't have wildcard privileges. There's also a set of topics that all start with $SYS. These are all administrative type topics that give information on the clients, messages being sent, and so on. If you are securing a broker, you want to make sure that these are turned off for all non-admin users as well. Revisiting this diagram, receiving information isn't like the request response workflow that you're probably used to. You are not requesting data and then getting a response back containing that data. Instead, you are subscribing to topics you want data from, and then when data is published to those topics, you receive that information. After you're subscribed, you'll continue receiving information on those topics from other clients as it gets published until you either disconnect from the broker entirely or you unsubscribe from that topic. There's also an optional small set of delivery assurance messages. We'll talk about that a little bit later. If we revisit our earlier diagram with topics, If the first client publishes something to topic 1, the broker is going to forward that on to client B because client B is subscribed to topic 1. It will also send it to client C because client C is subscribed to the wildcard and wants information on all topics. So if we talk about the MQTT packet structure briefly, all packets are going to have a fixed header that has information about the type of packet and then some flags relating to the packet type. There are a number of packet types as listed here. They come in pairs. For example, you have connect and then connect acknowledgement, publish, and then different types of publish acknowledgement, subscribe, suback, unsubscribe, unsuback, and then you have ping, ping response, and a disconnect. The next part of the fixed header is for flags, but that pretty much only applies to the publish message type because there are quality of service and other configurations that need to be set. Connect, subscribe, and publish messages provide more information than other types of messages and need to use a variable header in addition to the fixed header to include that info. For example, a connect message is going to provide version information, keep alive information, and so on. And then after the headers, you have any kind of payload information. Typically, you're going to see JSON, but you can do whatever you want, really. So here are two examples of Wireshark captures of packets. The first one is a minimal packet where it's 2 bytes and it is a disconnect message. And then we have a longer packet on the bottom where we are publishing hi to the Car Hacking Village topic. If we look at a subscribe message connection in Wireshark, the client is sending a connect command. The broker is going to respond with a connect acknowledgement. Then the client sends a subscribe request, and then if it's accepted, the broker will respond with a subscribe acknowledgement. If you're doing security testing and you can't get a connection to work, I suggest 2 different things. One is to use a -d in your subscription command, and then the other one is to set up a test server and get an idea of what a known good connection looks like. If a client has been able to successfully subscribe, after that you'll see a ping and ping response periodically between the client and the server as a keep alive signal. For a publish command, we have a connect, a publish, and then a disconnect message. If we had a higher quality of service setting, then we might get an ACK or other message back. And then the final publish line is from the broker to the other connected client. So once again, you can use the -d to get some more debug information. There are 3 quality of service settings that you can choose. 0 is the default. 0 is at least once. It's going to be fire and forget. There's no kind of checking or acknowledgement afterwards. Level 1 is at least once. It's going to keep sending that message until it gets acknowledgement back. At level 2, there's a little bit more going on, and as a result, you can ensure that only 1 copy is received. At this point, I think the best thing to do is to try out a MQTT broker on your own computer to see how it works. And to do that, I recommend that you download Mosquito because you can do all of this on the command line. There's very minimal setup, and I think it helps cement the ideas. First of all, you need to go to their download page and get it set up on your computer. If you're on Mac, you can do brew install Mosquito. Then you will need to start the service. I'm on a Mac, so I did the line shown here. And then you want to open up 2 more terminals. In the first one, you want to subscribe to a topic. For example, I had Car Hacking Village, and then the -i client 1 is my client ID. You don't have to provide this. It will make one for you if you don't, but just for completeness. And then in the other terminal window, You do a publish message to Car Hacking Village topic with whatever you want your message to be. I said hello world. And then in the first terminal window where you subscribed, you should see that data come through. Visually, that looks like starting the service. It will listen on port 1883 by default. You subscribe, you publish, and then back in the subscribe window, you see that you got hello world. If localhost is too boring for you, then you're in luck. Mosquito.org has set up a test broker where you have ports for each type of broker service. You can subscribe to all topics using the hashtag or #, and then use -v to show topic names along with the data, so you don't just get hello world, you get Car Hacking Village topic hello world. You can see this note on their website that says, don't publish anything sensitive because anyone can be listening. You probably know where this is going. Here are some screenshots from the other day where I have subscribed to all topics on the unencrypted port 1883 test mosquito.org server. We have what seem to be plain text passwords. We've got the lighting and temperature controls for some office. Probably most concerningly, an over-the-air update. And then this last person was just publishing basic C4 encoded images. A lot of the data being published here is probably junk. However, some of it does look important. A lot of times IoT projects or other projects that use MQTT will use a default value of test.mosquito.org as their broker so that the whole project will just work right out of the box. There's usually a note to change it, but of course not everyone does that. I have seen a production TCU unit that had test.mosquito.org commented out in the configuration file, so it can happen. Since this is DEF CON, I should probably talk about security. You likely noticed that in the earlier examples, including test.mosquito.org, there is a pretty minimal set of information that we needed in order to subscribe to a topic or publish information to that topic. We would hope that MQTT offers some kind of security features so we aren't completely wide open to anyone who can guess our IP address of the broker and then sees port 1883 open on their Nmap scan. As with the Mosquito test server listings, there are different levels of security that you can set on your broker. For the lowest level, which is the default, you only need to know the host name, port, which default is 1883, a topic, including wildcards, in order to subscribe. Technically, you also need a client ID, but the Mosquito command line tools will make one for you if you don't have one. By default, MQTT does not require authentication or encryption. You can set that up on your own. You can also set up authentication without encryption, but as shown in this screenshot, that means that plain text credentials are visible if you can sniff traffic. So hopefully that isn't enough security for your connected car architecture and you want to do a little bit more. So the next thing to do is to add encryption. We can do MQTT over TLS. We use a certificate to encrypt traffic between the client and the server, which means no more plain text credentials. Random people can't connect to your server. If you try and connect without a certificate, the server won't even respond with an acknowledgement. Your data is going to be encrypted in transit, which is a significant step up in security. I don't think you'll see many car networks with unencrypted traffic. I don't know that you can say the same for IoT. Let's say you have a car network set up with MQTT over TLS. You still need to use defense in depth. If you were to buy a TCU off of eBay, you get console access, you dump the firmware, and now you have the host name, the port number, what a valid client ID might look like, and then the certificate. You could connect to the broker or server using that information. You might think that's not a big deal. You're just going to get information about that TCU. Depending on how you have set up authentication and access control, you might be able to get information about other cars, which is obviously not good. That means we need to employ some level of authentication. We already said that authentication is not required by default. You can configure your broker to authenticate clients. If you are using some kind of paid-for service like AWS IoT, they probably make this even easier for you. You can pass in a username and password to authenticate devices against a device list, but what would be even better than that is to have individual client certificates. Of course, this makes the manufacturing and provisioning process more difficult and more expensive, but in this scenario, if you were to buy a TCU off of eBay and hack it, and you set up access control correctly, you can only connect as that device. You can't guess other username or passwords, especially if you're doing something that is guessable, like the username is the VIN or the IMEI or something like that. If you have authentication set up, you still need to think about authorization. What kind of data or functionality should a single device have access to? Ideally, cars should only be able to see information about that car, not other cars in the fleet, and not system-wide information. If they aren't using individual client certificates, then the authorization might be based off of either the username or the client ID that you have to provide. You should try both. Brokers can be configured to disconnect clients that are asking for unauthorized topics. I don't know how common this is in the wild. For example, I know that AWS IoT lets you configure all kinds of security access violation rules, but I haven't actually seen anyone use it for production. If you manage to get connected in whatever way, what you should try then is to see if the broker allows wildcards. Can you use hashtag or # to connect to all topics? If not, then you need to have a little bit more nuance. Try connecting to, for example, from earlier, car data, and then either a # after that for everything under car data, or car data and then a plus sign and then topic names that you already know about from your car. For example, location, latitude, and see if you can get information that way. Just because they have restricted wildcards at one level doesn't necessarily mean that they have filtered them out correctly at all levels, so try a couple different permutations. You should also try the system level topics to see if you can find information about the connected clients. And then if they have locked down all of the wildcards, which hopefully they're doing, you might be able to guess what the other IDs are and essentially go through the same process, but manually trying out different VINs or IMEIs instead of making use of the wildcard. For example, if the ID is a VIN, you could probably guess other valid VINs or look them up somehow. They might also be using the IMEI or the ICC ID of the telematics control unit. Ideally, they're checking your client name or username or certificate to determine whether you're authorized to view this. But if they had to roll their own access control setup, maybe they've made mistakes somewhere. There are other security features that you could use, for example, the access control violation rules mentioned earlier, or a VPN to close the attack surface up even more. I haven't used these tools a whole lot, but I found them while making this talk, and I thought I'd include them. MQTT Pwn is a whole framework around MQTT testing. The second one is a fuzzer, and then the last one is less for security testing and more on the development side. It has a ton of great links for frameworks and client code and things like that in a bunch of different languages. It's a great resource. So, in summary, MQTT is a pub/sub protocol that runs on ports 1883 or 8883, depending on whether you're using TLS or not. You have one broker and multiple clients. In the automotive world, the clients are likely TCUs, but might be other things as well, like mobile apps. information is separated out by topic hierarchies as defined by each system. MQTT security is important because of privacy concerns. You have car location that can be shared over MQTT. You have car safety, if you can do remote lock or unlock, and then over there updates where if you're somehow able to get in the middle of that, you could download malicious firmware onto the device. Hopefully, again, you have defense in depth and you have other checks for that. But MQTT is insecure by default, and it is up to the developers to implement authentication, authorization, encryption, and access control correctly. And lastly, MQTT is something that you can use in car hacking if you have a car with a telematics component. If you don't have that, MQTT is also very common in IoT, so you might be able to practice some of these things with IoT devices you have around your house. I hope this has been useful. I'll be around in Discord for a little bit. Afterwards, feel free to hit me up on Discord, Car Hacking Village Jamie, or message me on Twitter if you have any questions or anything that I can help with.
All right, Jamie, thank you so much for the very interesting talk about MQTT and how our cars are connecting to the cloud. Really interesting stuff. If you do have questions for Jamie, she's in Discord, so she's watching out for any types of questions that you might have. So if you do ping her there, her name is Jamie there. So anyways, that brings us to a conclusion for CHV101 for Saturday for DEF CON. Tomorrow we won't have any talks for CHV 101, but we will have many talks on the track 1 and track 2 and closing ceremonies, the announcements for CTF. There's plenty to do tomorrow as well. Looking forward to seeing you there. However, for CHV 101 2020 COVID Safe Mode Edition of DEF CON, we are signing off. Thank you very much for being there with us. If you have any questions, we'll be there much longer. So talk to you soon. Have fun and have a good evening.